in addition to literature.
Okay, let's get started. Thank you everyone for coming bright and early on a rainy day. Really appreciate you coming down here. Firstly, we'd like to thank our wonderful team here who set this through. So Beatrice in the front, please stand up and wave. Beatrice is here. Andrey over there. And Andrey's helped us a lot. And Kostya, who's here in the front, has been our guiding advisor. So thank you for everyone for helping with this. And Hans, who's from NRF, who's actually helped us for all the workshops, including this one. So he's basically not sleeping for the last 2 months. So thank you for coming this morning. And I'll just start off very quickly with a quick overview of what is the purpose of these workshops. Hopefully those who are online can see this. Perfect. So all of this information is actually found on this website, aiforscience.sg. So we actually own this, and we're hoping to build from this towards a conference next year. So we're going to have a conference this year in July on the 23rd and the 24th. And some of the ideas are well captured by Hiroaki Kitano's Nobel Turing Challenge. Now, this is obviously the grand challenge, which is, can the Nobel Committee give an AI system Nobel Prize without noticing it is an AI system? Right, so this is the Turing test of Nobel quality scientific activities. So this is actually the purpose of his workshops. He's had about 3 or 4 of them. I attended the one in Japan along with Andrey and others in February. The first thing we wanted to do was identify what AI for science means. So many of you have probably seen the scoping report. Thank you for everyone's contribution in this. Basically, the idea here is that AI for science is defined as working towards scientific discoveries. So we are actually going for AI to discover new scientific principles, phenomena, or enabling discovery that is not possible before. This is different from research for AI or foundational AI. This is basically the development in AI algorithms by themselves, right? New algorithms that have come out, some of you are following these KANs are somehow supposedly better than MLPs. I don't know if that's true, but that sort of falls in the realm of research for AI. And then there's AI for X, which many of us are engaged in, but I think it's important to sort of separate yourself away from that. AI for X are application of AI, so existing AI technologies that can be applied for a particular practical problem, right? And there's a lot of this happening anyway. So the way this is going to work is we're working towards a grand challenge initiative from NRF, which is going to probably be later this year. And these workshops bring all the domain experts and the AI methods teams together to define this space. And NRF is really looking at a combination of top-down and bottom-up. So the workshops sort of build that community, hopefully, and identify grand challenges, and also some areas that are obviously of interest or of strength in Singapore. Right? So it's a combination of that. The additional considerations, and please do pay attention to this today, are data and computational resourcing that's required for us to succeed. That's a really important thing to, during our breakout session later, to identify what those needs and what those data needs might be. So this is the timeline. This is again, we shared with many people in the first workshop. We're working towards the grand challenge proposals in August or September. On the 23rd and 24th is the AI for Science NTCI conference. We are here with the thematic workshops, and we've had about 8 of them, and we have about 7 more of them from different domains. So about 15 or 16 of them altogether. There are study tips that NRF is doing along with the leaders in the government to various areas, scoping out what AI for science means in different areas. So we will assimilate all of the information from these thematic workshops and study trips for the draft foundation research capability report that myself and Professor Zheng in the NUS computing department are co-leading. So, but we will definitely reach out to everybody to get your inputs into this. So really that's what we're working for is a white paper for today's workshop that I will help collate along with Andrey, Kostya, and Beatrice to put it together, which will then be a part of the full foundation research capability. So please do give your input so that we can combine that information and make a good case for material science and chemistry. These are the workshops that are taking place. Please go check out the website, aiforscience.sg. And many of these people are here as well who've done different workshops in different domains. There's a few more that are upcoming, AI for education. We will end, this date is not final, sorry, it's the 27th of May, AI methods for science. There are a few more workshops in sustainability, etc., that are being scoped out right now. And the idea is each domain lead will sort of represent the workshop in this final workshop for methods, where we'll get our computer science folks and friends from AISG to come in and see the pitch from each domain, right? So we'll talk about the data, the compute resources, and what are the benchmarks, essentially, and what's the vision statement. That's what we will assimilate from today's workshop and present at this workshop to get buy-in from the AI folks. So this is how we're designing this, right? So really what we're looking for is quite simple. We're looking for a vision statement or multiple vision statements, define problem statements and targets for potential AI for science areas, right? Important to define the challenges and bottlenecks. Again, we'll articulate this better as we go along. Bottom line is we're looking for vision, data, benchmarks, and if there's a possibility of digital twins, right? And where do we stand for material science? So the idea is that AI enables transformative discoveries, not just incremental changes. We need to define what those transformative discoveries are. And then data sets that are available or need to be curated, as well as HPC resources that will be required for this to succeed. Here's an example of where AI for science sits. I'm happy to share. Maybe someone's online, kindly mute. AI for science essentially sits in between foundational research for AI and applied research. So here's just a simple example of what this might look like. So, development of foundation models with different architectures. Property-directed generative design is something we're working on. So, you can apply for particular domain spaces, for instance. And then you have the final, if you do succeed, you can then design a catalyst that's then taken up by perhaps industry or a collaborative scale up. So that's sort of the end-to-end idea. If you come up with a few of these examples and see that AI for science is the key enabler for this to happen, that would actually define it quite nicely, right? So later we're going to have these breakout discussions. We've actually identified different ones over here: functional materials, structural materials, soft materials, computational materials, and AI ML methods. We have also folks from HQ at A-Star, Zora, and Temasek. And please, if you can choose which table you want to join. We didn't want to assign you to any particular domain. And we have folks who will actually help talk about that side of that perspective as well. So again, we'll flash this up later. We have some scribes over here, our friendly people who are going to help us take the notes during that time. So please work with the leads. And again, I'll revisit this later on. For those who are online, unfortunately, the breakout sessions are not going to be easy to involve you in. So we want your inputs upfront. Please go to this pigeonhole .at, enter the passcode AI for MSc. And anybody here can do that too. And there are different domains that Beatrice has created. Please put in your questions. So before the breakout sessions go out, your questions are already in. So I'll flash this multiple times during the presentations today so that you can put your questions in for each of the domains. And then those questions can then be addressed by the breakout sessions, right? That's the idea. Okay, so I will stop there. And in the interest of time, let me hand it over to our first speaker, Professor Liu Bin, who's going to talk about AI for materials in our domain. Share the screen. Here we go.
Yeah, good morning, everyone. I'm a little in a rush because I have 3 events to go at 9. All right, so I am not an AI expert at all, right? But what I would like to share with you today is my research is benefited from collaboration with the AI experts. And AI really can accelerate the materials innovation and development. So if you ask me what AI can do for me as a chemist and material scientist, right, I can look into 5 possibilities, at least as of today. The first one is to help us to predict properties before we synthesize the molecule. And then it can also help us to actually design the molecule and accelerate the synthesis, which means particularly for organic molecule, the reaction synthesis is extremely powerful with the AI support. And then we can also link the material design with the performance. And more importantly, at the end of the day, after we do the validation, we hope to draw certain principles that will further guide our materials design and also with the help of the AI. So it's really a very powerful strategy, and I was going to share with you 2 examples. So what I'm interested in is a particularly special molecule. This molecule actually shows aggregation induced emission that is very different from the traditional fluorophore you are familiar with aggregation expansion. We're interested in this molecule because of the 2 particular applications in biomedical research and also in the organic electronics, where molecules largely exist in the aggregated states, that optical features will be completely or partially compromised. So in order to look for this kind of molecules, previously we just design the molecule, we do the synthesis and we test it, right? So it cost a lot of time and actually wasn't super effective. And we're interested in these molecules because they perform completely different from traditional fluorophores, and in many of the areas that we already proved that they are actually able to making a difference in terms of making things previously not possible to be possible or enhance the performance in many of the applications. Now, about 5 years ago, we started with something really basic and fundamental. We looked at about 356 molecules, 240 ACQ, and 120 AIE. And we are not really innovative in terms of methodology, right? We just leverage on existing machine learning technology, and we have 240 combination of methods. What we look into is the molecular structure as well as the molecular interaction and the consequence. After 7 rounds of the trial and error, we're able to actually create a simple platform that allows us to test and predict the molecular structure, whether any given chemical structure that you put into the system, it will show whether that's an AIE molecule or the ACQ molecule with the accuracy about 93%. And very amazingly is that this methodology can even design to be so precise at single atom level. So we're able to actually differentiate the molecular differences with a single atom. One is AIE and one is ACQ, and then we publish all the methodology in online with the community so that now everybody, if they're interested, just put in the chemical structure, it will help us and everybody to predict that molecule is AIE or ACQ. So associated with that, we wanted to go one step further to understand whether we can leverage on the AI to predict material properties and more importantly, to help us actually pre-design the molecules. So one example I would like to share with you is if we look into drug molecules, and particularly one type that we're interested in is the photosensitizer, which actually absorb the light and produce radicals. So from the domain expertise, we understand there are 2 parameters that are key. One is the energy difference between the finished state and triplet state, and the other one is actually the energy level of the triplet state with regarding to the oxygen. So with these 2 design principles, we again leverage on the machine learning, active learning. So in this case, we not only look into the existing molecules, we also rely on the first principle calculation to work on the molecules that are purely based on theory. So in total, we actually look into 7 million of molecule, right? And then with 5 rounds of the active learning, plus the 2 descriptors that we define with our human knowledge, eventually we're able to come up with 5,000 molecules that prove to be effective. And leverage on the ratio synthesis, we're able to come up with 10 plus molecules. That is to validate the prediction of the machine learning. And what is exciting is here that if we look at the optimal performance of these 4 molecules and we benchmark with the best photosensitizer that are used in the clinical setting, in terms of the capability to produce radicals, actually the machine learning recommended structures prove to be a lot more effective. So with this kind of machine learning empowered material design, so what we benefit is we now spend much less time in the laboratory to produce the molecule with the functions that are much better as compared to what we can have based on our human experience, right? So with this, I hope I at least show you with a real example that how important it is to work with the people that are really experts of the data, algorithm, and also AI to go forward. And throughout this collaboration, what we learned is that there are a few steps that are critical. The first step actually is whether there's a language model or any methodology that will help us to capture the data information in the literature. And more importantly, and most excitingly for the molecular level, organic chemistry perspective, the field actually is really developing rapidly. And as a consequence, now there are a couple of very mature models that can read literature, that can understand chemical structure, that can actually extract all the information as needed, which is really wonderful. So once that part is available, we're also looking to DFT calculations, whether that can be done as fast as possible, rather than traditionally it takes us a couple of hours, a couple of days to do the calculation. We need that because we are not going to have all the samples ready. We need to rely on some of the theoretical calculation to help us to regenerate new molecules. And that will come together with the existing molecules to form a much bigger pool, so that we will be able to test the system in a way that's very effective. And after that, there's something critically important, which is often missing in our materials community with the AI experts, is the validation. Because I'm a chemist, I care a lot about validation, which means no matter how exciting the modeling, how tremendously super efficient is the AI, if the molecules that design cannot be synthesized or proved to have the property as predicted by AI, to me it doesn't work. But luckily, we're experiment based. We are able to validate, and as of today, at least in my own lab, my own experience, that we are able to validate and able to prove that with the right methodology, AI data learning actually help us to make our job easier, our molecules more functional, and the success rate is much higher than before. Now, after I get all these molecules, of course, we are working on the application. So for the application side, I focus on diagnostics, means how I can design the particles or molecular probes that can help the community to detect, to visualize, and to do the treatment. And after that, how can we report the efficacy of the treatment? So that's more like the biological application. I don't think that belongs to the focus today. I think I will just end it here today. So I benefit a lot from the AI studies. And I really hope that our materials chemist community to collaborate with AI experts, machine learning, so that they will really help us to make our life a lot better and save a lot of time and energy and make the world a lot more sustainable in producing wonderful chemicals or molecules as needed for all different functions. Yeah, thank you.
Right, thank you. The event has to leave in 3 minutes and she cannot join the panel. If you have any burning questions for her, I think this would be a good time to take one question, 1 or 2 questions.
Yeah, okay, you can email me at any time.
Or you can email her at any time. Any questions from group? I mean, we had a chat this morning, so I'll ask you this, and perhaps it's good to share with the community. You mentioned about how in your lab you tie in everything from DFT simulations to synthesis to testing. And so perhaps you can speak a little about how you design that, especially in the area of small molecules, and then maybe how can we learn from something like this in end-to-end learning platform for other materials.
Thank you. I think I have a very luxury system which allows me to actually bring all this in one lab, right? This is not what I want to actually promote or broadcast. I think it's more ideal that some of us in different areas come together to work on the same project. That's more effective, right? What happened to me is I started with organic chemistry for biomedical application. And then suddenly one of my colleagues left, and then he had the student who's interested in machine learning, and that person is interested in working with me. So that's how I incorporate machine learning into my lab, right? So after I incorporate this person, and this person tells me that the existing molecules with the function that we need may not be sufficient. So we need to rely on DFT to do a lot of calculations to predict and add in new molecules. Then I thought that's a brilliant idea. So because of that, we added another person who's doing DFT, right? So this is how I kind of get things together, but I don't think this is the optimized way of doing it. It will be more ideal that like colleagues from HPC experts on modeling, and then we are experts on validation, synthetic work, and then some colleagues from computing with experts in AI and machine learning. That kind of team come together will be a lot more efficient and a lot more powerful. Right, so I just started to show that things can be done, but I will regularly also work with more people from different places to make things more effective. Yeah, thank you.
Right, thank you very much, and thank you for coming again in the morning. Okay, with that, we'll move on to the second talk of the morning series. Professor Kostya Novoselov was directing the Institute for Functional Intelligent Materials. Find it here. And somebody share.
Morning, everyone. I'll try to take as little time as possible, leaving more time for discussion. Basically, by the end of today, what we need to cover is the structured approach to how do we see what are the most important tasks in the application of AI for materials. And let me try to throw a few bullet points here, and you can strike them out or add a few new ones. And luckily, we've been already pointed out a few of them already. So, right. So, because the big problem now is that our technology become more and more complex. You talk solar cells or batteries or computing, so those systems become more and more complex every time. So it means that we start to use much more complex materials and structures in our technologies, and that of course puts a lot of stress on the simulation, on the development, on the synthesis, on the characterization as well. And I try to put a few ideas how AI can actually help and unlock those problems for us. And just let me try to go through those points. Like, so first of all, as you've been already mentioned, there is quite a bottleneck with the current computational methods. So we have Monte Carlo, we have DFT, we have molecular dynamics, all of them, or the most, and there is a usual problem that the most accurate ones are that slow, and those which are reasonably fast, and yet I don't think they're fast enough. They're not accurate at all, and it's really rarely that you can trust them. So one direction is that we need fast DFT, fast MD, maybe quantum Monte Carlo, but also we need the ways how to reliably connect and switch from one to another. So we need the new methods how to acknowledge and estimate the uncertainty and all the computation. Quite a lot of work is being done everywhere in the world, including I think in this direction. Some progress. Talk to me later if you want to know. And of course, that would potentially allow us to describe complex materials, which are materials with large unit cells, or maybe materials without any unit cell at all, like high entropy alloys, for example, or polymers or biological materials. But that's of course not the only panacea for the distribution of those materials. There should be new methods, purely AI beyond the fast DFT, beyond the fast MD, which would allow us to do it. Then the next problem is the multi-scale model, and that's really, there are only a few works being done also in AI for materials for that respect. So Lubin is quite lucky because she works with the molecules, so it's not really you don't need to think about the multi-scale model in there. But the moment you go into polymers, into crystals, into alloys, your properties are not only determined by the composition or by the chemistry, but also by the crystallography, but by the grain size and defects. And this is a new problem. This is not a new problem. It's been there for decades, people write books about it, how successful it's a good fashion. And I really believe that AI can probably help us doing something in that respect. Then of course, probably the most exciting problem here is the inverse problem. So rather than experimenting and incidentally coming from hindsight, coming with the ideas for the new recipes, all the new materials, can we put something deterministic here, and can we find the right material for the right property? So it would be wonderful if you have a system which has the way you type in your desired spectrum, and it will spit out the composition, maybe even the synthesis rule out of that. Again, some work is being done in IFIM. Kedar is the expert, Andrey, the experts in this area. So I think it's probably one of the cornerstones for AI for materials. And then we go a little bit beyond, which is the interest of IFIM in particular. So it's probably a little bit biased that so it would be really nice to go for to apply AI for complex processes for the dynamic systems like catalysis. So today we really do it in a very basic way. So you compute a few frames there, and then you think that's exactly the reaction pathway. So the dynamics of the reaction pathway is really far away from being described anywhere by any methods in science. So that would be an interesting direction for AI. And generally what we're trying to do out of equilibrium systems, again, in physics and material science, we don't have any ways how to represent those. We already see that AI can help us quite a lot in this area, and that would be a fantastic application for that. So just maybe just a couple of words. What do I mean by the dynamic system? So you all know that a few years ago, AlphaFold solved the ground state for the proteins, and that's a fantastic achievement. The point is that the reason why those proteins are so important and so useful and so versatile in our body is not because of the ground state. It's actually because of all of those excited states, the metastable states where they can catalyze different type of reactions. And what is important is actually to learn all the other metastable states and all the other transitions and the stimuli for those transitions. Again, there is some work being done in IFIM for this respect, and Xiaodong just published a very nice paper in this area. And but of course, so that's a big task for AI applied for the dynamic out of equilibrium materials. Now, this is a little bit. This is something which I didn't mention in my previous slide. I borrowed this slide from Stephen Dale, who is he couldn't be here today. He was at the NRF interview, but so he basically noticed that there was this publication which of course everyone noticed from Google. So they predicted 381,000 new stable materials. And so they selected, as you know, 58 best gases and synthesized some 43 of them. And so they were that they should be stable. They checked it on the powder X-ray, and then people checked for those powder X-ray, and basically concluded that unfortunately none of those 43 are new. So those actually correspond to already existing materials, and that's really I think it's really amazing stepping stone in understanding how we should build our AI systems. That's so there is a lot of on the not only on the prediction. And it's a great job. Don't take me wrong, but what needs to be predicted, not only the structure and the properties, but also the first of all the synthesis route, which is important. So that's another point for AI, but also it needs to be verified, and in that respect, I think we probably need to include in our program the verification step, the robotics staff, and in general all those robotic facilities for the large throughput experiments to verify, but also to put the missing points and to educate our AI with something. So that's I think we need to discuss how much can we afford, because it's a very expensive one. Now NVIDIA is so big that's I don't know what is more expensive, the robotics or the GPUs anymore, but still similarly expensive as the GPU. And then probably the last point here, so we're talking about AI for materials, and that's exciting area. What we're thinking about as well is the other way around, is the materials for AI. So it's becoming. I'm not sure if it needs to be in this workshop, but I'll just mention it briefly that it's becoming clear that more than computing CPUs or GPUs or TPUs, they're not sustainable for the development of AI. So we spend 10% of our, maybe even more of our energy on the computation. AI will take another 5 in the next 5 years. So it's becoming unbelievably expensive. My background is in quantum physics, microscopic physics. So I'm really interested how we can try to create new materials for the new type of computing, new principles of computing, whether quantum, neuromorphic. So Andrey is pushing for probabilistic computing, and there are some interesting results there. And so those are actually based on new structures and new materials, which hopefully can be designed with the use of AI, but then it will be a full circle clause where we will use those materials and those structures to be applied to speed up our AI as well. So I think I will stop here. Thank you so much. So looking forward to the discussion. Thank you.
Thanks, Kostya. Keep forward your questions, because I think we will have a time for panel discussion later. So I think that will be okay. Thank you. Our next speaker is Professor Xiaodong from NTU, Material Science Department. Slow his slides.
Yes, so very good morning, everyone. So it's really my great honor here to share some of our thoughts of our AI for science In the last few years, we work a lot combining AI and the data, especially for electrical sensors we do on this kind of device. And during this process, we use a lot of data really generated by the electrical sensors to this kind of sample fusion. But in fact, this is something maybe it's not really we call the data AI for science. It's more about the can be learned from the nature using this kind of find this kind of brain to handling data. But we also ask one question: how AI can help us to develop new science or to understand something really beyond human can do. So this is actually one really keep it listening. And also really, like what is just now Kostya mentioned. I mean, in fact, for the material system, the process itself is very complex. In fact, this is exactly the topic I'm going to share everyone. They are thinking about this kind of complex materials and the process. So in fact, this is something one could be go beyond that. Maybe I can show one example just recently in this complex process, how AI can help. I'm not sure how many people know about I'm not sure how many know about this news just happened a few days ago. So this is the Air Force Secretary, Frank Kedar. So he finished this kind of aircraft. It's an F-16, but this is an all AI power machine. And then again with the man handle this kind of F-16. These two flight aircraft just next to that, just 300 meters away, just by a low operating system. And then for operate for 1 hour, unmanned control. So this happened just a few days ago. And then so this is something give us really can conclude is really AI can really do a lot of things beyond what image. But question is, what's really important inside? How this one will be done? In fact, just give you two data, you will know how complex for just for this system itself. So in terms of software, there are more than 100,000 lines of this kind of software. Well, involved is some 21 this kind of test flights. First one. The data set of millions of data sets there. And then also very important, part of $6 billion program. So this is alien made this kind of unmanned aircraft happen. And then if you go more in deep itself, in fact, it's really kind of complex systems involved with aerodynamics. So this is well established propulsion, a lot of kind of engine related mechanics, robotics, sensor fusion, computer vision, machine learning, and so on. So this is something one is really kind of complex systems. But this is still relatively simple because with the latest last this kind of more than 100 years development of this aircraft, because we know many kind of process already. But in fact, in nature, even complicated. So this is kind of complex materials process. It's much compared with just this kind of all this kind of aircraft. Because this involves a lot of this kind of, not about physical process, also a lot of this kind of chemical process, also a lot of this information and so on. So I give you 3 examples here. I mean, in the catalyst, just of course I mentioned already. So it involves this kind of production, a lot of this kind of catalyst, process, scale up, in the complex material systems, composites, and also we work a lot of this kind of device fusion. How this is something one can help to improve performance, increase accuracy, process and so on. And the last part is actually we are doing in my group now to understand the bacterial plant systems. So this again, I believe I saw it's very simple, just a few components and learning. But in fact, it involves a lot of electrochemical process. Later, I just give you examples how such a kind of AI power electrochemistry will be help us distinguish to many kind of conventional electrochemistry process. And then in the chemical material itself, in fact, there are the 2 components. One is the complex materials parts. In fact, complex materials involve like this kind of separate molecule polymers, polymers, materials, metal materials, and so on. So this is important materials, but also involve process, how it's really being involved in forms. So this is something that we strongly believe AI really in the complex systems is engines for many new scientific discovery. In fact, this is just now being in the course dimension a lot. How we accelerate material discovery, optimization, simulations, and also other kind of relationships, especially you go for complex systems. And then, so this is one more example. In fact, go for materials process. In fact, this was just published last year from one group from MIT. So typically for this kind of metamaterials, this kind of developments, right? So of course, the structure itself relatively simple, but they developed a new algorithm. So this allows them to really build this kind of complex structure, have a beams, have shells, and also a kind of compound volume structure. This is a 4x4, this kind of cellular structure, metal structure inside. Because this case, they can simplify a lot of process, and they also can build even complex structure by this kind of algorithm development. So this is the material. But of course, this is just one example. There are many, many examples of this kind of how AI can really simplify also into this kind of materials design and process now. And then we go for another one, process. Process, physical process also involve chemical process. Here I will just give one example. Chemical process. So electrochemical reaction, pretty simple. People always have this kind of oxidation, reduction inside. But if you really look very carefully inside, it involves many different kind of components, starting from electrodes, active materials, additives, operation condition, electrolytes, and also system configurations. There are many, many more. The question is, one more, this kind of primary adding, you will need a lot of this kind of changes in this case. So this is something for electrochemical systems. It's kind of multi-dimensional complex systems really deserve us to really explore. And in this perspective, some people really explore this direction about how AI can help this kind of electrochemical process, starting for this kind of machine learning based this kind of electrochemical sensing, bacterial identification, and also the battery health evaluation. For this one, Tesla is doing a very good job. And the last one also is kind of metabolism again. So this is about electrochemical process. So this is something one people have done. And then we are also asked ourselves how to go beyond more. So this is something what we are doing in our lab is bacterial electrochemistry. So the reason we do this bacterial chemistry is really our purpose is very simple. How such a kind of process to involve this kind of increase plant growth and also possible to help this kind of carbon sequestration. So this is something what we now talk about this kind of carbon neutrality, also talk about carbon activity. And then why we not use this kind of nature process to help this kind of process. So that's this case involve a lot of this kind of electrochemical process inside. It's very, very complicated, think much beyond we are solving before. So in short, give you a few people, this is our understanding. How conventional electrochemistry, you can see for this kind of material design, the left side is about conventionally just try to see what's without a material effect. For the AI electrochemist can give us this kind of data-driven design, can accelerate process. People always argue material design can start from design to commercialization, take about 15 years. Now, because AI can reduce to 7 years to do the deployments. The similar case for electrochemistry with AI can really accelerate all the process. Maybe 2 times, 3 times, but no quantified yet. And also itself, in the analysis itself, traditionally we go over CVIs and also many kind of simplifications. For AI, use this kind of integrated machine learning analysis. Especially, you can really identify key feature, can distinguish medicine, you cannot really distinguish human. And also in scale-wise, you can see for the typical modeling, just a micro scale, but machine learning can go for extra scale, that is atomic resolution, go to the millimeter scale. So this is something that will be increased scale and also efficient. The last part is the sensing management scale. Again, it's still sensor related, but this one can go to the remote real time to do this kind of multi-model analysis. So this is kind of conventional with AI will be different. In short, so this is something I understand from conventional one, is more this kind of discrete and slow process. For AI, electrochemists, we integrate and also fast process. This will be how it will be different. So this is something we are on the way. So of course, we really want to work closely with the ecosystem here and how we can really use the AI tools to accelerate this kind of process, understanding, and again, return back to really redesign whole kind of process as well. So I'll take this stop here. If any question, answer later.
Thank you. The next talk, we'll come back to question later. So next presenter is Chen, again from the NTU Material Science Department, who's going to talk about pre-materials.
Okay, first of all, I would like to thank Kedar, Zheng, and Kostya for making this happen. I really enjoyed that help from the previous three speakers. Okay, I'm going to share with our work and ideas on how to use AI for the design and fabrication of advanced materials. Okay. Next. Cannot control. Oh, okay, thank you. All right, so we all know that for the organic material, right, we have a lot of multivariance from the equipment, different equipments, and also we need a lot of times for trial trials. But considering the time consuming and the manpower consuming is unrealistic, right, for our experimentalists. Although it's doable for image parts, which will result into a huge this is this design space, and also we have to correlate this property and the structure operation for the optimization. Okay, so here's the challenging, but you know what? In the past decades, how many material has been discovered by AI or by machine learning? Here's the percentage. So single numbers. My number first at the very beginning is only 1%. But it turns out the number is almost 1/3. 33% of material has been discovered by AI in the past 2 years. So this is a big achievement, right? Because of this is computation capability has been doubled every 1 year. So in that sense, we're able to use AI to discover new material and also for the optimization of the organic synthesis. All right, taking off that at the story, right? We at the very beginning we have troubles in making the 2D materials. We found that for every run we are not sure the material can be grown. So we are using the XG model. We built AI structure architecture we call this is progressive adaptive model. And using that model with the quite limited data sets, we're able to grow the molybdenum with a very high success rate, which is more than 8%. And this is only one output, right? And then in the further work, we figure out that that AI model can also help us to engineer the structure of the material as the tungsten diselenide. We figure out that the feature of hydrogen is most important, which can help us to tune the film-like tungsten diselenide into the nanowire structures. And even move forward. We found that the AI can help us to realize a multi-objective optimization based on this hydrothermal based carbon counter loss. And in this method, right, we found that by tuning this is parameters, we can realize the full covered emission from this counter loss from infrared to the purple. And as well as very high PL efficiency, which is above 50%. Okay, I'd like to share more visions. It's not enough, right, for us to deal with AI for a single system or simple system. So can we use AI to tackle with some more complicated systems, such as high entropy alloy? So high entropy alloy consists of a lot of elements, right? Look at the periodic tables. There are tens of elements. Even when you eliminate some risky ones, reactive ones, we still have 20 or 30 members or elements there. So the design space is huge. Is it possible for AI to simplify this design space? And then we can fabricate this at a low density as well as high mechanical strength high alloy. And on the other hand, this is about the chemical composition, right? At the micro scale. And on the at the macro scale, on the other hand, on the micro scale, for the material itself, we have so many kinds of materials, some semiconductors, superconductors, and many kinds of properties, right? is it possible to generate a way that we can correlate the structures, crystal structures, to the properties such as the 2D case, right? And here we believe that the Prof technology might be a very useful approach to realize this. And okay, it's still not enough. Correct. I asked myself, is there any way that we can make a universal AI platform for all materials? I call it the triple A. So we know in physics, there's a mother theory for everything we call M theory. So in AI for materials, do we have such kind of theory? Is it possible? All right, so we believe that, okay, if you look at the trend of the material discovery history, right? We are now in the AI-driven science, data-driven science. But if you move forward, the ultimate form, here we call this as AI 2.0 driven science. So AAA, a universal AI platform for everything, for all material. But here are some key issues. The first issue is the data scarcity, right? Data scarcity. There we go. In order to address this issue, we need to generate more data, more good data, high quality data, or reliable data. Which, okay, I believe the autonomous and also high throughput method will be the key. The second issue will be here the diversity of materials with specificity of AI models. So the key will be general reliable approach within one model.
Projector online is okay.
Okay. Within one model, we can predict every project, every property. I'll give you an example. If we have this kind of model, we ask the model, I want material A for application B. The model will tell us, okay, I can recommend the material C, D, E for you, right? Okay, we can recommend the material C or D or E for this proposal. All right, that's good enough, but we can move forward. Model can predict material. Can model help us to create this material? So this here, this autonomous ways can help us do this. And this is also not enough. Although the AI can help us automatically create the material, are they good for the application? So we need the AI to give us explanation. So that is the second key, the self-explainable. All right, this is pretty much I'd like to share with you about our visions on material by design. I'd like to take any of your questions. Sorry for late.
All right, thank you, sir. Appreciate that. Can I invite the speakers to please join us on the stage here? Kostya, Xiaodong, and Yuta. Come back, please. Great. So I think we had some really nice talks this morning with some vision. Maybe I can throw it to the audience first because we didn't have any questions. So did you have any specific questions for either Kostya, Xiaodong, or Chen that you wanted to ask? Kevin, you want to start?
Yep, sure. Thank you very much for your talks. Really nice. I have a question for the three of you because you both alluded to the same thing. You did say specifically, Kostya, that you need to implement like checks and verifiers to make sure that you have indeed discovered something new. I'd just like to know what you mean by new, how you define something as new, because at least in the slide that Kostya showed, some people claim some things, others replied others. So what do you think?
Have you got the microphone? Okay, so honestly, at this moment, I don't even think that we need to focus on new or not new. So the problem with material science that we are bound by the laws of nature and by the symmetries which are possible, which are not possible. So there is, I mean, we do use ChatGPT in material science as well. And so Andrey is trying to apply it for the tight binding model and so on. But there is a difference that there are some physical restrictions which we have in our world, do we want it or not. And so any predictions from AI needs to be bound by the rule of our world. Three-dimensional, two-dimensional, one-dimensional, but there are bounds. So those are the first point of verification, that when you predict some material, that then it should be at least it should exist at least. So I mean they do test the fallen modes. That's a good test, but I'm sure that there are more things which you can test. So then the second step is whether we can synthesize it or not. The synthesizability is an important step. Not many people do it. There are companies which do have the software which tells you the synthesis route. I still don't know how good it works or not, but that would be, of course, a dream if the same AI process would give you something, would give you a way how to produce it. And okay, and then the new, well, it's for me, if we solve those two problems, whether it's new or not, I'm not sure we can. It's the secondary task, so we can verify it somehow.
If I may, I'd like to add something. I believe that new means the two folds. The first fold is new material, new chemical composition, and new processing from AI. And the second fold is new mechanism, new science, or new reactions. That's what I favor from the AI, but I believe we need some time to take this.
So maybe adding a few more points, at least from my experience, for new, it means we don't know before, right? And then in fact, this case, any kind of things, because I think the scientific knowledge of we understand is still quite limited. Compare the nature, it evolved in the last, not only something, not very 10-something years, this kind of developments. And then give you example for this kind of, we spend a lot of effort to do this kind of soil research, right? In fact, soil itself is a very complex material system. Involve a lot of this kind of electrical chemistry process and also photosynthesis process. In this case, a lot of things really beyond traditional textbook can tell us solving. And this is also the AI can help us, because AI really, all this kind of ChatGPT, all this kind of large language model and so on, can really summarize a lot of this kind of knowledge we may spend 20 years associated to learn. But now in just a minutes, you really can really summarize all this kind of knowledge for us to build up on top. Then we can really accelerate this kind of materials, all this kind of process discovery. This is one perspective how this kind of AI can really help us to do this kind of science. But another angle, I think that many people didn't really do to think too much. Now everyone use AI, everyone use data. My question is, if you think about this need electricity, need energy to power this kind of data set for them. In this case, we may go to another extreme directions. We are going to not have enough energy to support all this kind of AI, all this kind of data center. So this will be go for extreme worst case is really this also against the so-called kind of carbon neutrality. Overall this kind of initiative there. So this is something maybe also for AI for science to go to another direction. How our scientific discovery to really help us to decrease kind of energy consumption. Maybe another one can be used this kind of just user mentioned already, smart network system. Such case, they could really use less data, but can do much faster this kind of scientific discovery. This one case. Another case, maybe you also need to consider about develop new kind of computing architecture, new kind of algorithm. So this is also a part, I think, is AI for science can help us in this step. So this is mentioned. Thank you.
Thank you. Any other questions from the floor? Well, I can kick off because I had some questions that also come up quite a lot in discussions. So we've had various stakeholders asking these questions, so I'll ask you these questions. Right. One of them that came was a central theme was that we need to embrace the complexity of the problem, right? In materials, that's something very specific. That's perhaps not true in other domains, and the dynamics perhaps that determine the functionality. So maybe I can ask you, if we were to build an AI for science lab in the next 3 years, what would it look like? Not in hardware, software, I understand automated labs, etc., but the people who will drive this and what's missing that perhaps as this initiative goes forward, is something that we make a call for, it's something that doesn't exist. Yeah, maybe, so put simply, what does a future AI for science lab look like in your mind?
So I guess you already answered this, that what is missing in the world, so how things been developing in the past few years in AI for materials is first the very simplistic application that we can predict the properties of existing, you just generate with certain code some random structures and then optimize it and then see how we can optimize this process to the stable structures and then predict their properties. So that's more or less the straightforward pathway. Everyone are doing this. The inverse design, when you start with the properties, it's of course it's a dream. Lots of people are working on this. Some success still limited. But then if we think about the way how we use our materials, and we usually use them in systems. So and in that respect, so that's exactly what Xiaodong been talking about. The vision that we really need to understand how the material is behaving in the application in the dynamic system, and then it leads to the simulation, not all the material only, but actually all the whole process, all the application itself. And that's, I think it's really exciting problem. It's not only exciting from the point of view of material, but also from the point of view of mathematics or physics in terms of complexity and how the complexity arises and how we can dissect it into, or whether we can dissect it into smaller parts. And I think it would be important to think about about materials on the system level. So I guess, and that would really put us unique in the world if we can think about multi-scale and complex systems, complex processes, bacteria or catalysis. So that would be very special. I don't know. I mean, we had some thoughts how to do it. So far, it's been done through completely separate AI. So one AI, neuromorphic system, designs your material, and another one analyzes the process. So it's I would say at the moment it is done on a very naive level. Whether we can come with something more exciting from the computer science point, it would be still the same.
And my personal feeling is the most important thing is still data. Okay, because experimentally data is quite scarcity, and we need high quality data from ways like you mentioned robotic way, right, high throughput ways, and also from the simulation. This one thing, and the second thing is so couple the model with physical laws. Like Kostya mentioned, the multi-scalable or multi-dimensional ways, right? Newton's law, quantum mechanics, or some. We have a lot of physical laws that how can we embed into the AI models that can give us precise prediction of the result. And this is most important for me.
I think not only, I mean, I'm very confident AI can really help us a lot of this kind of scientific discovery. I think there are two concerns, I mean, I think we need to be very careful. One part is, in fact, just not Kostya mentioned about this kind of validation or verification. So this is something where as long we have a lot of this kind of set built up, how to come to validate, what is this kind of verify. This is one side, and then how we can do it. Another part, I think, also be very, very careful, I think, where's the boundary, Now we can see for all this kind of AI can really do a lot of stuff beyond what we can see before. We can see for just like solar unmanned aircraft. But a lot of unmanned things can happen, right? I mean, in this case, we we needed to ask ourselves, we are really in a safer place to stay. We are really be very careful, for this one part. So this case, for AI for Science Lab, we need to ask ourselves, what will be the boundary? Because we are very confident we can do many things happen, but where's the boundary? Maybe for this kind of ethical issue, how we can develop this kind of trustable AI, and also how we can trust AI for science. And then we don't want to develop this kind of science at the end will be destroy or damage a lot of this kind of potential, this kind of leading a lot of this kind of risk. So this is, I think, my personal opinion as well.
Thank you. That's quite interesting. I think I just mentioned on the data side, because the question is that we have to generate the data as we test it.
Yes.
And perhaps that's also a problem for the AI machine learning folks to say that, hey, you start the data, but what's the active learning method by which you get to that exploration faster? That's the comment I'll make on that. Any other questions? Marcus, back.
I just want to make that's okay. People online.
Hi, good morning, everyone.
Please introduce yourself.
I just want to add something to the discussion. And people who know me won't be surprised what I'm not going to say. But what is needed on top of the AI models is knowledge representation. If you want to address the explainability point, if you want to address the consistency of data sets and you have a high dimensional model at a larger scale. So we were mentioning material, say, finite element code or something like that, that is based on parameters that come from, say, first principle calculations or mathematical dynamic simulation. Then there is a need for consistency. And also, many people across the world work with quantum tools like VASP, Kostya, et al. Okay, there is enormous. You were mentioning the enormous cost that arises. What if all these calculations were at your fingertips with just a search command? Okay, I think the future, if this is done properly, and we've been thinking about it in CARES upstairs, then that in its own right could reduce the number of calculations you have to do. But this is just the search. On top of that, the rules you find by just number crunching AI models, once they are poured into explicit knowledge representation, then suddenly it's much easier to traverse the search space. Okay, if you go to a chemist who has decades of experience in the lab, these chemists will tell you what is possible and what is not possible. He will or she, or whatever they, this person will be able to just guide you through the synthesis space. And I think once we are able to extract this type of knowledge and make it explicit, then we can work on the other space, on this explicit space, much, much less expensive. And there are ways of doing it. And I think this is a component that I would definitely like to see in the future AI.
Absolutely. Any comments on that? Knowledge representation, I don't you have.
Yeah. So I completely agree with you. We had this experience a couple of years ago, a year ago. We created our own data set of impacts, and then we put it online and try to put extra data from other groups into our computational data set, and try to put the data from other groups there. And then you quickly realize that it's impossible. So it's impossible to compare any data in the literature simply because people use different functionals, people use different unit cells, people use different boundary conditions, different gaps between the layers, and so on. So by the moment you put all those restrictions into your data set, you understand that it's impossible to use it for AI. So that would be a big task on the synchronization and on standardization of the data which you know.
Perhaps the way to do it is to start by incorporating this from the beginning somehow.
Maybe I share an opinion, I agree with the also just now mentioned. And for data set, we always also like publication, right? We always publish what we are building, the best performance or even a high performance. But in fact, a lot of cases I'm not sure we any city paper publish mistake or something doesn't work out. So this is something, in fact, even this kind of doesn't work out, this is data. This is really help us to understanding models and systems. In fact, we discussed a lot as a journal, I'm editor-in-chief of SSNano. And in fact, I thought I'm really open to or prepared to publish some papers just to ask why it doesn't work. Not always tell people why it's all work, why it's always best performance. So this kind of doesn't work data will also help us discuss accelerate a lot of understanding. So this I'm not sure will be potentially also for this kind of data science as well.
Yeah, avoiding the bias is quite critical, I think.
Yeah. I have a comment about the high accuracy aspect of this. But I think as a matter of strategy for AI in material science, more fruitful strategy may be not to aim for high accuracy. Actually, it should be the other way. We should aim for even low quality data, but a lot of data. So we should aim for trends. We should aim for getting multiple properties at a given space and fill up the gaps using, say, physics or other phenomenological equations or fast computation, which is not necessarily so accurate, so that we can identify, like a filter, those domains or those areas which we need to look at with higher accuracy. So I think, if we look at a AI for Science lab and we look for high accuracy data from the outset, that may limit the output of the space that you can explore.
Any comments on that? I think it's a very good idea because the uncertainty in a way needs to be taken care of. So I'll take two more questions from the floor. Bala and Yongwei, they already raised their hands. Sorry, guys. Let's start with you, Bala, first.
Thanks, Kedar. I see there are a couple of today's session. There are a couple of mentions about the dynamic molecules or dynamic systems. Right? And so my question is about what's the challenges in using AI in dynamic systems, as well as is there a problem the data collection itself because of the dynamic nature of the molecules?
Yeah, that's good. So one thing is ask Kedar, so he published the paper recently and also experimental. So I'll leave it up to him, and which was so really impressive comparison and link between experiment and the simulation, which surprisingly worked for a change. But then so there are two answers here. So one is we have you can do it one route through MD and really hope that if the start and the end if the boundary conditions are there, so the start and the end match in the experiment, usually very difficult to observe the dynamic process. But you can observe the beginning and the end, and then if you hope that if the time is right and the statistics of the time is right, and then hopefully the process inside is correct, and you do the modeling with MD and you try to extract information from there. But then of course there is another way, and which is to observe the special points like metastable states, which are always appear in those dynamical systems. Those are easier to observe experimentally. And let's hope that if you find the energy structure or the metastable states for that system, if your AI predicts it correctly, then hopefully the dynamic process is predicted correctly as well. So those are my only ideas. I'm sure that there are many more.
Just a few words, right? This reminds me about the missing part of AI model. Actually, dynamic system is high time dependent, right? And time dependent means we have cause and effects there. And currently, most of the AI models, such as the Sora, which can generate a video, there's no cause and effect. So, which means we have to invalidate the logical, the physical laws inside into the model so that we can have reliable data.
Take one last question from Wei. There's a mic there. Hopefully it works.
It works. Wei from HPC. Last question actually in responding to Jim's question regarding high throughput in not that accurate data and high throughput type of calculations and high fidelity data from high fidelity calculations. So in parallel, we can talk about the foundational data, like the ChatGPT. It's basically very knowledgeable and they can answer general questions, but when you do in specific topic, then it's become less accurate. Now in the science in our domain, right? Should we develop a foundational AI model for science? And then we also develop specialized domain AI for specific domains. Can you give a comment on this?
You should answer that.
Okay, well, we're actually putting a proposal together. I think the short answer is we need to try. Right, we don't know the answer yet, right? We need to try to see if there's such a thing. I don't think I'll speak about this later, but we don't have a foundation model for all of material science. That seems to be ridiculous to me. So it has to be something for alloys, something for polymers, perhaps, that can then transfer. So we need to try, and then we will know the answer.
Yeah, just look at this slide, right? I'm very fascinated by this slide. So look at the fourth paradigm. Then it's basically human dominant and human interact with machine means methodologies, and then become this paradigm. Then human becomes silent. Yes, right? So human become redundant. That's the way we should go.
Yeah, I think we leave that as a question for the coffee break. I think there are a couple of questions online, but I think we will answer them because I'm sorry guys, we'll answer them by text. I'll talk to the experts and we'll get them answered. But so I think let's break for coffee for about 10 minutes. I think it's 10:05, so 12 minutes, coffee outside and breaks. If you have further questions, please come up to the panel. Thank you very much for the morning session. Very, very intriguing. And see you in about 12 minutes.
Yes, thank you, everybody. So next up, we will have Kedar, Professor Kedar from NTU and IMRE to share with us solid state materials.
Thank you, Beatrice. Okay, I'm just going to get started. I think we've heard quite a few of these themes before, so I just wanted to reinforce why AI for science is kind of critical. And again, emphasize that those discoveries that are only possible with AI, high efficiency, self-driving labs, literature-based discovery. So I think we're all familiar with this. So I'm not going to belabor this point. I would just like to mention that the investment in this is quite large. Eric Schmidt just announced Future House, so please do take a look at this. This is focused on, let's say, drug molecules, drug discovery. There's a Chen Zuckerberg Institute, which actually has dedicated large computing resources. It's led by a Stanford professor, Stephen Quake. He's the head of science. And that's also investing a very large sum on discovery on synthetic biology. So for each domain, there's substantial investments. And in Singapore, we probably have to identify carefully what our positions of strength are and focus on those, right? So I just wanted to highlight, because we spoke about validation this morning, that this example here that you see on the left-hand side is an interesting one. So Microsoft Research, which has a program on AI for science, came up with a sort of funnel approach, the combination of multi-scale simulations, starting from DFT all the way down to prediction of properties, and identified some materials that should be synthesized. And in PNNL, the Pacific National Lab in Seattle, in Washington, they actually synthesized the material with 70% dust lithium. One of the problems, and perhaps this is something discussed during the panel discussions, is the lack of transparency when these big companies start to get involved in the research, because nothing actually has been released in the public domain about this apart from the results. Right? Something we should perhaps discover. But the motivation is clear. Just to mention a background and what we have done over many, many years. I think many of you might have seen the slides or have been involved in this. We have actually done a combination of high performance computing, automation, machine learning, AI. Again, this is segmented AI, just like Kostya mentioned. It's done in silos. Either we do optimization algorithms or machine learning potentials. And what we have demonstrated in about 20 to 30 test cases that acceleration is indeed possible. So we started with various different sectors and demonstrated that this is actually possible both in industry problems, in a startup, as well as different materials applications, right? And here's an example of how this works. In reality, is that you have multimodal data, which is essentially what people are talking about these days. So essentially, you collect oxidation states from XPS. You look at the uniformity of the film in hyperspectral imaging, and you're able to make sort of fully automated workflow for the synthesis of the materials, and characterization is in different locations. So I think this vision is shared by many people in the room, where you actually have automated stations, as I like to call them, which are data driven, and then you string together the data and have either physics-based models drive these sort of efforts. You can do integration of this. This is actually being done in IMRE at this point. So integration means that you do still have various different tests. So UV curing, thermal, dynamic mechanical analysis. Some of these robots actually didn't exist before. So in order to measure the properties fast, the team actually invented new robotic tools to do this. But you can build them in a modular fashion and have a single footprint. The vision of this, and Pablo's here, one of the people driving this along with Chase and IMRE, is to actually build this on a single footprint in a breadboard sort of configuration, right? So those are doing optical experiments. You can imagine modules being put together and make it fully integrated if necessary. So the question often comes up, when do you automate a materials process? And my opinion here is that you automate it once your process is fixed. So you need to figure out what is your final process, including DFT perhaps and simulations with machine learning. And once you've figured out what the final process that leads to discovery is, we are then in a place to actually make it integrated and fully automated. This is the work that Kostya is involved in, and Li Chen Xiao from the mathematics department led the work, because Beatrice here built the experiments along with some collaborators in IMRE. You can see that this is actually the unfolding electrokinetic stretching of a DNA molecule. And we can collect about 400 data points in a matter of a few hours. The challenge here, what we did manage to do is that because it's a stochastic dynamical system, we're not able to predict the unfolding rate and the metastable states in between a priori. So the algorithm that Chen Xiao built actually allows us to do that, to identify the closure coordinates, so the thermodynamic coordinates that determine the system. So it's a really elegant approach and demonstrate how AI architectures can be evolved with the physics in mind in order to solve such problems, right? And this is really, I think, what you would call AI for science, because you're developing both the algorithms and methods to solve challenging problems, right? Now, the challenge here, though, is that we can collect a lot of trajectories, but the system itself tends to give you, let's say, biased data, right? You get unfolding, and then it's very easy to do fast unfolding, and reaching those metastable states doesn't occur statistically as often as you would like. So you need to actually collect a lot of data and filter through it in order to look at the full potential landscape of the material. So even with an automated system, you still need, speaking to Yongwei's question earlier, you still need the human in the loop to decide whether you have the right bias, right representation of the energy landscape or not. So essentially what I will end with is that, you're only as good as what you measure, especially in material science, because the complexity is very large. And so we actually build all these modular robotic tools, both in A-star as well as in NTU for different applications. So this is what we've done so far, right? So now I'll go to the question that's asked, right? The question I get a lot is, how far are we from AlphaFold to materials discovery? Right? You cannot believe how many times I've been asked this question. The answer is we're already there. right, is the paper that Kostya mentioned. The genome paper, as was discussed, 380,000 supposedly stable materials, and the wording that's used is, 800 years worth of knowledge, blah, blah, have we solved the problem, right? The answer is no. And I will give you a counter example of why this is not the case, right? So anybody here recognize this video or image? Okay, great. So anybody working in glass perhaps would have, but this is Dow Corning's lab to make Gorilla Glass. And if you think about the composition of glass, it's silicon dioxide with some ions inside, more or less, give or take, right? But the key here is that they were able to focus the stresses at this point where basically molten glass, of course, of the secret composition, comes together from both sides. And the way they do it in the velocity at which it comes together concentrates such stresses in such a way that it's really hard material that does not break when you drop it from a certain height. So composition is just part of the problem. The process innovation is really key for you to achieve this functionality, right? So you can then think of it, okay, how much can a machine do and how much can a human do? The variables for AI optimization, the composition and process, but the human innovation is discovering this fusion forming technique, right, which came from many, many years of domain expertise. So I think this kind of process innovation and including that in your material discovery loop is going to be very, very critical, right? So what can AI do well today, right? It can do predictive modeling. I think we heard a few of these today, a few examples of this. Given a database, can you predict the structure and the performance of a material? Yes, we can. The methods are pretty robust and mature today. So we perhaps do not need to innovate too much. Inverse design and multi-property algorithms, very different optimization, etc. That's almost there, right? The tools are pretty good. They are being evolved as we speak. But validating them is the key, right? So the algorithms themselves are pretty robust at this point, and you can use them. AI can also process literature data and computational workflows, speed up simulations, right? So and we all of us use this at different levels, for example. So LLMs have enabled that because of natural language processing. Computational workflows are automated at this point in many cases, even to get multi-property. So look at inequilibrium properties of materials. You can actually use nicely strung together workflows. AIDA is a good example of this. So, this is actually possible because of AI and machine learning based potentials, etc., to speed up simulation. So we can collect data of different levels of accuracy and fidelity quite fast. That's already, AI is already pretty good at this. So what can AI not do well yet, right? I think generative design, in some fields it works well, in others it doesn't. I'll give you an example of this in the next slide. How to make the materials, I think this is really unsolved. Linking with experimental labs, innovating new processes, maintaining the flexibility to making new things is really challenging, right? I think for sure when you think about that extremely deeply, right, to get that. Property-directed generative design, Kostya mentioned this morning, out-of-distribution properties, out-of-distribution input spaces. Okay, that has not been solved. I think that's also a very interesting area that we can work on. And then solving issues with scale-up in manufacturing, right? We had a whole workshop on AI for manufacturing, both on the semiconductor side and the bio and the chemical side. So I was here. And essentially, we can do materials discovery, process discovery, but scale-up is a value of depth. Can you actually use machine learning to scale that value of depth is also an unsolved problem. So I think we really have work to do in this space, and hopefully we can bridge all this. So what I wanted to do was to sort of summarize this. And again, this is a question that came. If you think about materials discovery, there are two parts to this really, right? One is structure, or let's say composition, and function, right? Maybe that's the way to think about it. And then we have different classes of materials, so small molecules, drug molecules. I put them as a special case because they're quite advanced. As many of you probably heard, drug discovery and design is quite advanced in this state. Proteins, polymers, alloys, glasses, crystalline materials. Maybe there are others I missed. I apologize if this does not capture everything. But let's think about these, right? So let's think about structure and function for these, right? So for small molecules, this is at Bruker. Once you've solved the structure itself, the small molecule, which there are many databases today that are really good, very large data, millions of data points, sufficient for machine learning models and deep learning models to work. You can get forward model prediction, inverse design, no problem. But you're not solving the issue because you need multi-properties, affinity, selectivity, mode of action, synthesizability. And then this is just in what they call target validation stage. There is actually, when you go to drug molecules, you need to actually be able to do clinical trials, which is a systemic level problem, in a bio system, and there is no really good data that does that. So you can get all the way to, let's say, clinical trial phase 1, but there are about, if I'm not mistaken, about 13 drugs that have already been discovered through AI and validated in the lab, right? This is already a success story. And the last step of the clinical trials in humans, which needs to go to animal trials in humans, is not solved yet, right? But perhaps it's a hit rate question. If you have 100 such things that go through, if the hit rate is 10%, you just need to have 100 AI discovered drugs, you accelerate the process overall. Maybe that's the answer, I don't know. So proteins, I think Kostya mentioned this very eloquently. So it's not just the structure, it's the states that you go through that determine functionality. Polymers are even more complicated, right? So the polymer is, take a monomer unit and repeat it n number of times, but the structure of the polymers through all the self interactions and interactions with, let's say, your solvent, and let's say you extrude it in a certain way, it's a plastic, is a many to one problem, right? It's a very difficult problem to solve. Do we have data at this level of complexity? No, we don't. Can you simulate data at this complexity? No, we can't. So that's actually a serious problem. Alloys, right? Alloys are actually sort of semi-crystalline materials, I'd say. There's some level of ordering. This is actually Raju's paper that I collaborated with, and the idea here I wanted to highlight is that it's multi-property. So you can take alloy compositions, but you need to collect data. And this particular work, Shakti was a student in this, spent a couple of years just collecting experimental data on iron, cobalt, nickel for 2 years, curating the data, imputing that database, and then doing experimental validation. Right? So it's a really challenging problem. And this is basically a different class of materials than glasses, right? Glasses, as I mentioned, is silicon dioxide, but you have to have multiple properties that industry cares about, like transparency, strength, transmittance, and so on and so forth. You really have to collect the data in all of these spaces, or at least have proxies for them in a physics-driven way, so you can innovate. Crystalline materials, this is somehow a crystalline material. It's a hybrid perovskite material that many of you work on. I'm working with Nippon on this in his team. This is the carbon-based solar cells. You can see how complicated it gets from a material discovery to a device discovery stage. Can you do that end-to-end learning? Okay, so I guess the point I'm trying to make is that it's not sufficient to do materials discovery. You would have to think about the functionality, and perhaps the word that was used this morning is a system-level design to solve these problems. So where are we in this journey, right? So given that I've given you examples of this is my opinion that the steps you need to solve are represented here. Is the unit representation, right? That's basically, can you featureize the molecule? Can you featureize the protein? Can you featureize an alloy? And I think there is definitely work that's been done in all of these spaces. Structure and stability databases, it's there. But for instance, if you look at alloys, maybe it's binary and ternary alloys at most, because the composition space is so vast that it's impossible to capture all the complexity. So we need to spend time on collecting those databases. Multi-property databases that determine function, right? Again, you can see small molecules, drug molecules are reasonably advanced. Proteins are definitely advanced, but I think here's where polymers, alloys, classes stop. So I don't think there are many examples of generative models for these. Maybe the inorganics are a little bit ahead of them, but not much work has been done on generative models in that space. This question is actually something that Microsoft's vision is. They have a whole center on AI for science in Germany that they just started. On their idea is that you have to have an emulator, which basically means it gets you 95% of the way, and 1 or 2 shot learning is sufficient for you to make it. I don't think that's true for most material classes. Perhaps it's true for small molecules and drug molecules. But again, this is something up for discussion. So is it synthesizable or makeable is a multi-dimensional challenge. Closed loop synthesis, I think maybe there's little dots here. There have been some illustrations of these in different domains, of course, but it hasn't been done end to end all the way. And then when you go to manufacturing, then there's prototype, product, and scale up. So I think only when we get all the way to perhaps this point have we solved the materials discovery challenge, right? So perhaps we're waiting for this to happen for any of these in order for us to say that AI for science has succeeded. Sort of something I wanted to present. So we're working on this. I'll just take a couple of minutes on this. We're not working on everything under the sun, but some inorganic material spaces, specifically focused on catalysis, because we have an area of strength over here based on 2D materials, looking on some of the thermal barrier coatings, as well as looking at quantum emitters, right? We have some data that starts us off, and people like Andrey are building foundation models towards this. So this is a recent proposal that we put through for materials that is in the final stages of approval. It definitely falls in the realm of AI for science. And the proposed methodology is that you can actually have various different properties in your target learning branch. So once you collect the data, you should be able to do property directed design. This hasn't been demonstrated yet. So people in my team are actually working on this for inorganic materials at this point. But I think it's just bringing together all of these experts under a roof will actually enable us to do that, right? And so I like this particular slide that my team helped me put together to show that you can take existing databases, you have to have representation, structure, bonding, which is the physics of it, structural stability and phase stability. And when you're relatively confident with multi-loops inside, you can then hand it off to rapid experiments that then validate it. And that includes property, composition, and structure. So all this is a large loop, which is end-to-end learning. And when we have this framework for one particular application, right, we're going to try and do 3, as I mentioned. So you need to have this sort of loop figured out in the beginning for each application, and then you're well placed to solve this problem. So I think I'll stop with that, and I'll pass it back to Beatrice.
All right, thank you, Prof. Kedar. Next up, we have Dr. Teck from IHPC, sharing with us about computational methods.
Right. Thanks so much for the invitation. My name is Kedar. So I'm heading the material science department in the IHPC. So I'm a computational material scientist by training, so I can't help it but to show this diagram. We show the various kinds of simulations that can be done over different length scales and different time scales. So we all know pretty well the epidemiological methods, which can be based on quantum chemistry or quantum mechanics to be able to predict the properties of materials. And when you try to scale it up to various length scale simulations, you can, the next scale could be things like molecular dynamics, Monte Carlo simulations, and going up, you could have coarse grain models and mesoscale methods such as phase field and plasticity models. So I'm citing some examples from structural materials design and also for chemicals design. And of course, ultimately, when you go to the continuum length scales, you can leverage on methods such as finite element methods, FEM, and also for the fluid side, like computational FD. So each of these methods has its strength and drawbacks. So we know that epidemiological methods can relate very well and is actually predictive of the material structures and their properties, but because of the quantum mechanical nature of it, it's pretty computational expensive and typically we use workstations or like supercomputers like ACRC and NSCC to do these computations. Right. So in order to understand materials and their properties at scale, then you probably have to do multi-scale simulations, such as, for example, in the coarse grain scale and the mesoscale, we want to be able to predict a collective phenomenon. Because we know that, based on physics, the observables of the material is based on the collective behavior. So we have to simulate the kinetics and also the thermodynamics in order to understand what is the behavior of this material. And of course, when you go up to the length scale, then we can talk about things like processes. How does the processing impact the microstructure and how microstructure in turn affect well properties? So if you're looking at this, yes, we have a spectrum of material simulations that is able to address problems at specific length scales and time scale. And naturally, one of the way we use machine learning in a materials and simulation is to bridge length scales. So for example, we could make use of the lower length scale simulation as a source of data to train, to parameterize your parameters for the higher length scale simulations, and also using machine learning surrogate models to speed up the calculations, for example, to solve differential equations in some of these methods. And this is a set of slides which also mirrors what Kedar was presenting, because materials is very broad. So we could have design and various methods which is applicable for different classes of materials from inorganic crystals to catalysts to polymers and also to semiconductors as well. I think the point of my slide over here is to say that for each of these classes of material, there is some attempts to do multi-scale simulations to predict the properties, because we know that for some of these materials itself, we can't just stop at atomistic first principle calculations because their properties are dependent on the collective behavior of the atoms and also the processes itself. So various groups worldwide have tried some of these multi-scale simulations. Like for example, in for alloys, there's always that multi-scale simulation chasing the dream of integrated computational materials engineering, IMRE, in order to do multi-scale simulations of metallurgy properties to include like predictions for state, phase stability, microstructure, and how it impacts properties. And likewise for chemistry and catalysis, polymers, and electronics materials. And of course, this is a slide to say that, okay, so when I started to do DFT, first principles calculation, I was very excited. I thought, wow, with first principles computation, since it's such a predictive method, right? So, and given that computing power is always scaling up, can we one day really screen through all the possible materials and compounds in the periodic table and predict their properties? So I would say the answer is probably not yet. And that's why we are talking about using some informatics approach to do this. And when we talk about informatics approach, so one of the things that DFT, this kind of simulations can help us is to use modeling and simulations to create an informatics database which can be used to train your AI models. Right. And this is just an example using catalyst design to showcase why it's not really possible to just make use of modeling and simulations to screen through the huge design space. So if you're looking at catalyst design, one of the things that is very important is the catalyst structure. And the catalyst structure itself is very complex because it's not just about the catalyst itself, but also the interactions between the catalyst and the support and the catalyst with the molecules. So that is the materials part. And then there's the functional part. So on the second quadrant, you see that if you are studying a fairly complex kind of chemical reaction system, like for example, conversion of CO2 to like fuels, wow, there is a lot of reaction pathways that needs to be calculated. And each of these calculations is very expensive. So it's really not possible to use a brute force computational approach to screen through all these reaction mechanisms. And to add on to the complexity, you could have chemical environments. If you try to model electron catalysts, they put the solvent effects and all this as well. So the short answer, it's not really possible to do a brute force modeling and simulation approach, even though computing power has scaled up very much. Right. So so the approach that we are talking about here in the workshop is really to how do we merge AI, modeling and simulations, and ultimately high throughput experiments in order to combine forces and use that for materials discovery. And this is a slide to say that we have already started this initiative worldwide since the Materials Genome Initiative that's declared by Obama in 2011, whereby once we make use of informatics approach, high throughput simulations, high throughput experiments in order to build up a database, right? So as Kostya and Kedar and many other speakers have pointed out, through these efforts, yes, we collected a lot of information about databases, but each of the groups has maybe different ways of representing them, have different preference for which properties to calculate and the ways to curate and represent your data itself. And in that, some of these efforts have led to well-known large databases out there. Like for example, for inorganic materials, there is materials project database. with about 150,000 compounds and their properties, OQMD likewise. And also for catalysts, there's this open catalyst 2022 databases, which has about 1 million service adoptions. And over time, as these databases grow larger, then we can talk about leveraging data-driven approaches to discover new materials. And yeah, and these are some of the details about things about using some of these databases to build materials-based features to train our AI, and also using them to predict composition, process, structure, and properties relationship. And during that era, about 2015 to 2020, most of these AI and machine learning efforts are really more task-specific in nature. And I think all these models incorporate very well, but how about extrapolation? So that's extrapolation is always the key question. That means you train on this set of data, but is your model able to extrapolate out of this train zone, right? So in the recent years, yes, because of this advancement in AI, especially in generative AI, LLMs, large language model. So we are now talking about out of distribution predictions, as Kedar has pointed out as well, and things like foundation model. Is there some kind of foundation model, a representative model that can bridge between structures and properties, and ultimately to processes and other scale up properties as well. And that has led to some paradigm shift in terms of R&D and materials discovery. So if you look at the first column, so we used to rely a lot on human judgment, on our deep experience as a scientist in order to recommend what is the next set of experiments to do. And in the past, with the high throughput experimentation and simulations, we are very gung ho. We said that we're going to do as many simulations and experiments as possible to cover the material space. And now we know the limitations of both methods. So over here itself, okay. So when we have enough of this materials information, it comes to the conversation of how do you integrate all these things, simulations, experiments, and AI to come together to tackle this materials discovery challenge. So indeed, over here, if we are able to harness all the information out there, be it historical data, be it our own data generated in-house from experiments or simulations, then we can build an AI that's hopefully can encompass and learn from all this knowledge base and use that to recommend materials, and you can do some level of in silico validation, and after that, further down select the most promising ones for experimentation. All right, this is just to showcase some of the large materials databases out there. So one of these is materials project, which is pretty well known and is developed in Berkeley labs. So these are the statistics, and you can see that how much time was invested in the building of this database. So 100 millions of CPU hours per year, right? And of course, it's not I also share some other materials databases, and of course, this is not an exhaustive list. But you can see what I'm trying to point out is that materials databases, they can come from different sources, and they could have different kind of informations, and some of them, if you're talking about the data qualities, so I think Prof has mentioned about the fidelity. So in terms of materials data, we typically think of quantity-wise, maybe not so much as compared to other AI applications, but we really stress on quality, right? So there's a trade-off between quality and quantity, right? So we could have a lot of large numbers of low fidelity data and maybe less so for high fidelity data. So how do we manage this kind of data spectrum in order to maximize the accuracy or robustness of our AI methods? So that is one question that you might want to ask. So that is the quality, and of course, some of these databases over here, they are quite task specific. So they are trying to address certain properties and materials characteristics of the class of materials and for the for particular applications. And right, so this is just one example on how some of these in the materials AI community have tried to leverage on large materials informatics. So, for example, we have seen the community try to develop all these these kind of how should I say, maybe AI models. Some of them are based on graph neural networks, but it doesn't need to be that. Some of them could be based on LLMs to train on all these rich, very rich materials databases. And so I highlight one example here, which is the M3 net developed by Leong from UCFD. So the idea is this, right? So you train your neural networks on these hundred thousands of compounds, and typically you can gain a speed up of 100 to maybe 1,000 times of the DFT calculations. And the hope and the holy grail is to think that, okay, if we have enough of this data, hopefully can the AI model replace DFT calculations itself? So this is just to illustrate that to some extent, if the AI model is trained well enough and seen enough information, there's some hope that this kind of large models, models trained on large data could maybe one day reproduce the DFT calculations. And going on, this is the slide to show that with in this age of informatics, AI, modeling and simulations, and lab automations, how we could imagine, right, using all these methods and information on hand in order to design new materials. Like for example, this is a work by Prof. Zheng, looking at structural alloy design for additive manufacturing. So you can see that if one wants to go towards this kind of integrated kind of modeling AI and experimentation, we typically will need to have some level of machine learning, which helps to narrow down which are the compositions, which are the materials to look at, and also to perform at a higher length scale the processor, the impact of processors, and how it impacts the properties itself. For example, in structural materials, microstructure is a very important determining factor of your mechanical properties. So being able to model very accurately the microstructure of the alloys itself is very important. And from there, we can further down which are the important process parameters and compositions for experimental validation. And so this is the third time in this workshop we're talking about genome. So indeed, so these are the recent developments. So we know that again, genome, which is being trained on these large material databases like Materials Project and QMD is, and then after once you do the AI model, you can use it to generate many stable, predict many new crystal structures to be discovered. And A lab, which is in Berkeley itself. Okay, so this slide is just to capture our imagination. So if AI is able to predict, okay, so reliability aside, if AI is able to predict this number of structures, like at what rate can we really verify all of them? And should we really verify all of them? Yeah, so if you're looking at some of the top-notch automation lab, which can do like testings of samples hundreds a day, you probably need 10 years to cover all these predictions. So it's really not realistically possible. So there will be discussions about, okay, so we have 381,000 structures, but how many of them are really, really possible? So you could imagine that we need to apply even more filters to help us to focus and help us to filter down which are the ones that can really meet our needs, yeah, and applications. And these are some other examples as well. So besides genome, there's also robo reaction or chemistry. This is really more for small molecules discovery. And there's also an open catalyst project itself. So some of us who are working on the catalyst materials design, this database itself, based on modeling and simulations, has about 1.3 billion structure to catalyst structure and adsorbents information. And of course, on the bio side, we have this bionet as well. And to summarize, this is a more forward-looking slide. So if you look at what is happening around the world, and also based on the conversations we have, so in terms of what are the key challenges and opportunities for materials, AI, and informatics? So for data itself, we are challenged in terms of the data sparsity. So the amount of information that we know on the material space is actually quite small, pretty small indeed. And we have also a data variety in terms of their quantity, quality, and variety. And it is so because we have both experiments and simulated data, the materials data is also in different modality as well. And that actually pushes us towards to think hard about data. Is this, when we are curating our data, is it findable, accessible, interoperable, and reusable? And this also means opportunities for informatics and AI, right? So we have really thought about all these large models trained on large material databases, and therefore it comes to the idea of foundation models. Can we come up with AI models that is generalizable to different classes of materials? And also, how could we leverage generative AI for our distribution predictions and doing inverse design? And of course, large language models have captured our imagination. And how do we harness it, say, for extracting knowledge from literature, and also use some of these text-based generative and using LLMs as a new text-based or generative models for material science. And I think another aspect which might be interesting is transfer learning, because we know that materials can be used for so many different applications. Can our knowledge of alloys being used in structural design can it be used in, for example, catalyst design as well? So there's some of these conversations that we need to have in order to progress this field. And I think this is the last slide. So if you think of how we can use data and informatics to accelerate the material discovery process, perhaps we can think of how we can break down how we can break down the steps for material design, starting from deciding what to make, how to make it, and verifying if we really make what we intend to make in the first place, and how good is the product, and all the way to scale up. Right. So these are some of the books over here. And this is the last slide where I leave you with an imagination. So again, this is for conversation as well. So let's say if you want to discover materials in an autonomous way, using an autonomous lab, probably we will need to develop some kind of informatics foundation. So for example, our data, which can come from external open source data, in-house data, will form our data source, and that helps us to build up the informatics layer. And from there, perhaps we can develop different kind of operation models, and then we can build various pillars for AI, for example, AI for synthesizability, performance, and maybe scalability in order to support our autonomous share for materials discovery. Right, with that, thank you.
Thank you, Dr. Daniel. Can we have a final speaker from Andrey from ITIM to give us share about foundation model?
Okay. Thank you very much for inviting me. So, and in this talk, I'm going to give really a high-level overview of foundation models and how those are applied and can be applied in various contexts of material science. So, the first point I would like to make that science is broken in many domains, and communication between those domains is doesn't come easily. So you need to understand topics from different domains. You need to understand what does the single phenomena or term mean, how it is expressed in own domain language. So and one of the success in the recent development in the foundation models is the ability to speak on languages, almost any domain, which was included in the training corpus of those language models. So, and in a broader sense, I'd like to highlight the main topics, how AI can be helpful in scientific context. And of course, it was mentioned many times already, but I think a really nice expression of this is mentioned in this paper written by many scientists, and Alan Proguzik as one of the contributors. So there are threefold of AI applications. So the first one is like a tool, microscope, that you can use to make predictions, to analyze data, etc. Right. So and then we know it is used in this context and in really many different domains, different models. Secondly, it is a muse. So it's kind of a source of inspiration that can, for example, read literature, understand methods that developed by people in one domain, and suggest how those methods can be applied to your domain of interest. Or it can read some literature, understand some gaps that are not filled by research and by some concrete result, and suggest focus attention of researcher on this particular gap, right? And then thirdly, as AI can serve as agent of understanding. So that helps to develop theories, to validate theories for certain kind of phenomena. And there is kind of understanding is very vague term. So and this is a very concrete expression. What can be meant by understanding actually, without metaphysical terminology. So if you have a theory T of some phenomenon P, so this scientists can recognize qualitatively the characteristic consequences of T without performing exact calculations or experiments. So it's kind of validation criteria that you can derive from this expression to see if there is understanding inside the model. So and when we think about foundation models, so first of what we need to mention, so it's essentially a pre-trained model on a vast corpus of text or data or whatever. So it's a bit more scientific way to understand what are foundation models. And of course, it comes with a large scale, either learning capabilities or training data. So it should look broadly across perhaps different domains and different scales. It should be adaptable through fine-tuning to specific tasks. So if you train on one corpus of text from one domain and you add a little bit of your own specific domain, so you can get inference in this new domain as well, an ability to generalize across different domains as well. Presumably, semantic understanding is also required, so it could express what are the main concepts, how those related, if you're talking about text. And scalability across complex computations that allow to address some multi-scale issues, multi-scale problems. And I would mention also multimodal integration. So it would allow to text image of a molecule and translate into a text representation, and then vice versa. So working with tabular data, images, text is also kind of cornerstone for foundation models. And continuous learning is something that is a wish, and foundation models should be able to perform this kind of updates in transparent way. So here are some examples, starting from generic foundation models like Llama, GPT, DALL-E, so that we use on daily basis. But of course, there are some domain-specific foundation model that has been developed for biology, for chemistry, and many other fields. So I will give example of one of the foundation model or application of foundation model in chemistry. It has been quite a while since it was published, and probably it's not the best example, not the most accurate one, but I just wanted to highlight the context and possibilities using this example. So it performs tasks given by user, and agent is composed of multiple modules that exchange messages, access to APIs, access internet, and able to run the code. So it's kind of multi-purpose agent that is trained to synthesize chemical compounds given instructions by natural language. And the design is happening in some hardware environment, hardware lab that this agent was able to connect through APIs. So in the tests, it was given examples how to perform certain tasks in natural language, and it is able to do those very accurately. And so the commands that it was able to perform were about synthesizing some compounds, and some of the compounds was synthesized correctly. Partially the knowledge was taken from the data, from the training data. Partially it was taken from the open sources, like from internet. And interesting is word of caution here is it was able to prompt it to synthesize illicit drug that it was not able to synthesize with straightforward prompt. So it was challenged to synthesize some kind of drug, tetrahydrocannabinol, and the change of the prompt was to add for the reason that it was performed. The synthesis should be performed by DA licensed facility for animal trials, which this sentence was absent from the previous tries that were failed. But as they add to the prompt, then the synthesis was performed successfully. So it's kind of safety concern that we have to keep in mind dealing with such models. So speaking of applications of foundation model to scientific context, you could characterize or break into several categories. So the first one is text comprehension, which is like the most obvious thing. So you can let the model read a lot of papers from different domains and find some similarities and give insights about what can be possibly done, what was done in similar way in neighbor domain, like it was done in quantum chemistry, how it can be applied, for example, in physics or quantum physics. So, also, it helps to apply AI in low data regime. So if your domain has low experimental data availability, it's still possible to exploit a large model that was trained on something bigger to your particular case. Also, it is possible to generate code for simulation and analysis and integration of integrate LLMs for knowledge representation was also mentioned by many speakers before me, that there is a huge gap between different databases, different data representation, knowledge representation, so how to mix them. And like previous approaches based on some a priori semantic definition of ontologies and some ways how you express unstructured thing in some kind of structure were not very successful, not very ubiquitous. In case of LLM, there is a hope that it will be possible to do otherwise successfully. And of course, as I shown, it is quite easy to integrate LLM to help with working with different APIs and optimize experiments and some protocols to design new kind of materials of molecules. So also mentioned by many people before me, that the name of the game to a great extent is design of multi-scale model that can span across different time and dimensional domains. And partially the solution for this problem is the way how we can coordinate efforts across different labs, institutes, across different groups that possess different expertise in AI, in chemistry, and material science, and design more powerful and more comprehensive models. One of the examples of collaboration is Rosetta Commons. So it's a collaboration across 100 universities, and they kind of manage to produce meaningful results like simulation packages, design models, and many others, leveraging collaborative funding across Europe, UK, US, and many others places. So, and one of the cases that can be also taught in this context as helpful is organization of competition among wider community. So there is one example that is running currently on Kaggle. Sorry, here's the point. It's called Mathematical AI for Mathematical Olympiad Prize that essentially addresses the incapability of current LLM to reason about mathematical expressions, mathematical terms. Another interesting case is a hackathon that was organized in 2023, I think, at FFL, that explored various capabilities of LLMs for material science. And as a result, that there is a paper that covers various applications that was developed in this context. So here I highlighted some challenges that I think are important for foundation models. Is the design of novel computing architectures for more efficient training, and curation and unification of data sets that would help to train such models. For domains, there are a bunch of approaches. I would just highlight a few of them. So approaches and challenges. So the first one I would say is reasoning. So how model can produce some meaningful conclusion out of some inputs that you give as something that is known. So addressing novelty in research directions, given the literature, given the all the papers that published in particular domain, what can be discovered on top of this? What would be the most interesting, the most influential discovery given what is known already? And of course, multi-scale ability. So how can we train a model that is not only can reason about different domains, but how can it go from quantum level to macro level in some meaningful way, especially given the fact that there is no single path. So it's for different goals, you need to go different paths from quantum to higher level. And of course, safety and trust concerns that should be also taken into account when we talk about such powerful model, how to keep a collaboration of humans and AI entities on healthy relation. So with this, I would like to conclude without reading this title, just to save the time. So if you have time during the panel discussion, we have to address the question. Thank you very much.
Thank you, Prof. Andrey. Can we invite all the speakers, Dr. Zheng and Kedar? We'll start the panel discussion now. In the interest of time, maybe we'll limit to 3 questions from the start, and we'll leave the rest for breakout discussions. If anybody has any questions?
Hi, Joel Leong from Zora Innovation. Thank you for the great talks this time. I want to stress the critical point, which I feel everyone's mentioned foundation models, and we love them. I love to have my own foundation model, but we know they're expensive, right? We know that by definition they're trained on vast amounts of data. In contrast, we've learned that in the material science discovery world, we've suffered some sparse data and a diversity of data. We also heard on Monday from the semiconductors workshop, and I believe it's also the case in material science, that there's a lot of proprietary data that's protected behind company firewalls. From the research academic point of view, how would you propose solving this problem? Are you proposing to build a foundation model within the academic community? Where do you think the next foundation model is going to come from? And I ask this to speakers and to the room. So.
Just the first naive thoughts is that the data that is available currently for individual domains, like for material science, for molecules, is large if you compute it, count by numbers. It's maybe diverse and not well aligned with each other, unlike text. So in case of papers and textbooks, so you just need to copy them together in a big data set, and you can go training like LLM model or BERT-like model. You need to put more efforts in like aligning different data sets in the model and propose maybe some format, some representation of the data that would be like suitable for majority of labs or big deal of labs, so they can contribute to this format. And also I would mention efforts of not just data sets, but benchmarking of models that are trained on those data sets. That is kind of missing nowadays. Or it happens in very fractional scenarios, some very narrow niches. But we would be, I think it would be helpful if we could see what is the model performance on particular data set for particular tasks. So it's also kind of relevant to curation of data sets. Maybe there are other ideas.
Well, I can quickly add, right? I think you mentioned, let's say, the features of what a foundation model would look like. I think the 2 key questions here are: is there enough data? How much of it is proprietary? I think there's an opportunity to innovate. Foundation model has a property that you can transfer with very little data to a new domain or a related domain, right? So it's up to us to actually develop a foundation model for limited data. It's not billions of images, but it's millions of compounds and processes. So I don't think that's the bottleneck. And proprietary data, yeah, for sure. There's proprietary data that, experimental data that companies have that they will not give you access to, but I don't think it's like the semiconductor industry, because you can we actually have many open source databases for certain properties which are developed by labs across the world. And in principle, you can validate a foundation model based on that data. So I think it's not the bottleneck again. That's my hopeful view.
Just to add on, so from a modeling simulations perspective, so we have open source database like Materials Project, OQMD. So there'll be a question about like, okay, maybe there's a question about like, if you train your foundation model on large data sets, then there's a lot of issues about the energy that's needed to train such foundation model. Okay, so I think like for text, like ChatGPT, because there's a lot of information out there, but if you compare the amount of materials data out there versus like text-based data, is significantly smaller. So at this point in time, probably not too worried about the energy usage of training such large foundation models. And you can see that there are already attempts based on 100,000 of this model estimations data that's using like graph neural networks to train on all this data itself. And the second question is like, how do we make use of this? Okay, then the second question is about reusability. Let's say if we train a graph neural networks on this large materials data, can we use it for our own needs? So we can also model the kind of strategy used in some of this ChatGPT. ChatGPT could give you good answers, but may not be accurate answers. Let's say if you have specialized data, you can retrain your foundation model on ChatGPT so that it's more specialized and be able to adapt to the kind of questions or specialized knowledge that you need. So likewise, you can adapt this foundation model from material science. And let's say if in your own lab, you have higher fidelity data, but for a particular class of materials or particular class of applications, can we tweak or retrain this foundation model so that it's become more specialized and be able to answer your questions for your own research?
Quickly add just one more thought. So there are methods that allow you to train a model on a data that is not exposed to the owner of the model. So there are owners of data, owners of models, and there are ways how you can send the model to train it on some like encrypted way of this data set and send back to the owner. So and this actually gives the opportunity to companies owning private proprietary data sets to give it away maybe for some fee. So researchers can, if they see there is a possibility to exploit this proprietary data set, so they can collaborate with this owner of the data and get the model that is aware of this data, so that it's kind of currently happens in peer-to-peer basis, but it is possible to make it more accessible for designing of knowledge representation and some like meta model of the data in different places.
Practical question. So I'm sure that this question about the foundational models have popped up in every single workshop which you run. So we have the creation of the foundational model, and then for material discovery, for drug discovery, for finance. How much is it in I don't know, computing hours or man working hours, the creation of the foundational model and then tuning it for each of the specific domains? Is it, I don't know, 80-20 in percentage, or is it 10-90 or 0-100?
Yeah, it really depends on the amount of data you want to like add to this fine-tuning sample. So it essentially quadratically proportional to the size of the data you want to add. So if you want to add a small like
So
1%.
But is it now all about adding data, or is it still about creating architecture?
Well, mostly adding data. So the architecture, so there are different ways how you can enrich or fine tune the given foundation model, but architecture is like given by the design of the model and fine tuning processes. There are several models like low rank representation or just regular fine tuning, but still it's pretty, I would not say solved question. It could be also topic of own research, but in most cases you just need to follow the recipe.
I'll quickly answer. What I've heard is that 90% of the effort is in the training, and then about 10 is for the retuning and new data coming in. So that there's a initial investment in the training of the model, and then it's really fast to adapt if you think about it carefully. So we've heard so far. Maybe the numbers are not fully representative, but it's about that ratio.
You guys will take our last question.
Right there.
Hi. I just want to kind of merge the first session where we talked about multi-scale modeling, as well as this current session where we talked about foundational models. So do you think foundational models for material science will work with multi-scale modeling, such as, of course, we have the materials project, we have the materials genome where we predict stuff like your quantum properties, then we move on to your grain size properties, maybe predict grain size or other more micrometer scale properties, and we move on all the way up to bulk scale properties like yield strength and so on. Do you think a foundational model will work in that case because of the difference in scale? Thank you.
Yeah, so that's a good question. So I might not have a gut feeling for this, but you can imagine that I think the first step we might want to look at is that we get data. So for each of the scale, we should be able to get corresponding data. Let's say if I start off with a certain materials and I want to maybe know, for example, the tensile strength, right? So we should follow through in terms of multi-scale simulation so that there's correspondence, right? So that when I build out my database, there's a correspondence for materials A, because of through all these multi-scale simulations, it has a tensile strength of so much. Because right now, this might not be totally harmonized because each multi-scale simulation groups might be doing, these higher length scale simulations for materials A. But then obviously people are interested in materials B, and therefore the data doesn't quite sync up. So I think to enable a foundation model to be built, we need a consistent set of data. There needs to be some follow through for a certain class of materials processes. And then when you have enough and a balanced data set at each of these length scale, then we can talk about differentiation on foundation model in order to reach all the relationships.
Yeah, I would concur that that there is a huge room for improvement for foundation model that are currently focused on very particular scale, and I would say that the gap in the research for multi-scale foundation model is kind of missing. I mean, it's empty. There is almost nothing. So there are some approaches that indicate how it can be done, but to my knowledge, it's much less populated rather than single domain, large atomic models, for example. Of course, they can solve many tasks already, so you can ask for different things. But going from quantum to some dynamics or some high level physics, it's not possible. So you need to add something on top of it. Currently, perhaps you can do it in better way, more self-consistent.
I'll offer a counter perspective from the material science perspective. I would say that all of these dense scale bridging is your final property, right? So you go from quantum, which is DMT, let's say, to molecular dynamics and FEM. So that's the process to generate the data for the property of interest. There are already machine learning models that speed up each of those and perhaps bridge the length scales. So then it becomes a data generation process. So your foundation model is typically some sort of generative model, diffusion maybe, transformers, I don't know, VAEs, etc. And so once you build that data for the property of interest, then multimodal just becomes a fancy word, right? Because essentially multi-scale, because you're just building, finally your property is what you're after. So you collect the data for your final property of interest and then you build a foundation model. Maybe that's one way to think about it. It hasn't been done yet, I agree. So maybe this thinking is wrong, but that's what I was thinking.
Okay, thank you. Let's thank our speakers now, and then we're going to get to the discussions. We have approximately five different groups. There's the functional materials, structural materials, soft materials, computational methods, AI methods. We have guidelines for maybe where each of you might like to be, but feel free to move around. We acknowledge there's a lot of overlap. Please just try and, as you think along your discussions, just try to the overall vision. What are the grand challenges in your respective fields? What are potential methods for us to overcome this, and especially thinking from a Singapore's perspective, where might we be able to carve out a niche for ourselves? And what are the transformative outcomes that can come out of this? Thank you. Please go ahead, and we'll have leads on each duels. Guys, please contribute to the discussion. We look forward to hearing.
So please, I think we'll have to rearrange. Please join the tables. Maybe we can start with functional materials on the left, structural materials in the back, soft materials in the back over there on the right hand side, and AI method, ML methods over here, and computation methods in the middle. Please feel free to join any table. These are just suggestions, right? The leads are kind of experts in this. I did not see Xiaodong, so if he's not around, then maybe, I don't know, Zheng, Kostya, or Andrey can take lead on the functional material side. And then please walk around a little bit and settle in. The scribes will join you and they will actually take notes and try to fit your discussion into this section. On this, you can join the methods. So again, functional materials on the left-hand side there, structural in the back, soft materials in the back on the right-hand side, AI ML methods where Marcus is standing here, and computation methods where Kostya is right now. What? So feel free to join any of the tables based on your interest. This is just a recommendation. I didn't say anything. I don't know. Marcus is the bald guy in blue shirt. Okay, again, where Pepe is standing here, that's functional materials. I don't see Eleanor is in the back with her hand up. That's structural materials with Ram. Soft materials in the back on the right hand side. The smiling guy with the beard is Saif. Look for him. AI ML methods is over here with the beautiful pink shirt is Andrey. And computational method in the middle with Teck, Leong, and others. All right. We'll do force you guys to sit there for 40 minutes at least. And then please grab lunch and come in back inside. And the scribes will capture all of your information on the whiteboard as well as later converting into PowerPoint. Okay, so we're going to start with you guys. Yeah. All right. Start up. No slide? That's okay. Yeah, please go ahead.
Okay, so this is so I'm Saif Khan. I'm representing table 3, soft materials. So we had our first point of discussion was what we define by soft materials, and we arrived at a narrow scope, and that was essentially materials that are composed of polymeric molecules, whether they are natural or synthetic. So these could encompass things like block copolymers that are used in a number of different applications, or natural polymers. We're thinking RNA, DNA, proteins, etc. Essentially macromolecules, whether natural or synthetic. And the key thing to note in this definition of soft materials is the macromolecules composing these materials have properties. They are functional materials that are then used in a variety of different application scenarios, which I'll name in a second. So that was our definition. Now, the biggest gap, the biggest challenge, we were asked to identify a grand challenge. And I think this challenge is already alluded to in the previous presentation. So with macromolecular systems such as these, there is complexity in terms of their structures themselves. These macromolecules do not have simple linear structures. They have complicated structures, secondary, even tertiary structures, and they are dynamic, inherently dynamic in that these structures are constantly interconverting in the energy landscape as many minimum. Right? So typically, it is the structures of these materials as well as their assembly into higher order structures. We're thinking, for example, micelles for synthetic polymers or hydrogels, both of natural or synthetic polymers. These are even further levels of structure that are obtained, which ultimately dictate properties. So that was the application space we discussed. On our table, we had applications that were very wide ranging, ranging from performance materials in personal care products. Nearly every personal care product has soft materials embedded in them. Food materials, materials for sustainability, packaging materials that are biodegradable, for example. We had application case studies in protective materials, so armor type of materials, sensing, so sensing of, for example, volatile organics using polymeric materials. So the application case space is very wide. So the one grand challenge where AI can definitely assist, the AI for science can definitely come into play, is really filling that enormous gap between structure, the molecular formula, and the structure at the individual macromolecule level, and the performance, whatever that performance system does in all those application spaces, rheological, mechanical properties. These are physical properties that are a consequence of structure at multiple scales. There is a big gap there. So in going from understanding and predicting molecules to understanding and predicting their properties in performance scenarios. So that was the big grand challenge that we identified at the table. There is a big gap. Now, in terms of where Singapore can come in, I think we have both the expertise in various soft material domains, but we also have very extensive manufacturing and industry related to these soft materials. So therefore, the impact is definitely there. In terms of AI, well, okay, there are two things that come into play. This big gap between structure and performance can be filled by a combination of both experimental methods and AI methods. Let me elaborate. Even measuring the performance of these materials at high enough throughput is a big challenge. Measuring structural properties of these molecules is a big challenge. So there is one experimental piece there that definitely some efforts exist, as Kedar already highlighted, but there is a piece there that can be addressed and should be to generate the data that is needed. On the machine learning side and on the multi-scale simulation side, there is a lot of opportunity and challenges. One big simulation technique would be, for example, molecular dynamics, which was alluded to multiple times today. Doing molecular dynamic simulations at the length scales required fast enough to be relevant is a challenge. Therefore, once again, AI can come in there to accelerate the MD simulations to enable us to augment experimental data with simulation data to fill that or to bridge that huge gap between structure and performance. We discussed this at the table. There are then the follow-up challenges of whether these materials are indeed manufacturable in whatever way we conceive of that, but we didn't discuss that. So I think the one big challenge in soft materials really is structure and performance and that gap. And there is definitely a very large scope for AI to come in at multiple levels along all the parameters that were discussed in the talks. So that's I think what table 3. Anything else to add to that? Perfect. Yeah. Okay. Thank you.
All right, thank you. We'll go clockwise from 3, and we have a table over here, which is ML methods. Nothing back there. Slides, yeah. No.
Okay, so I'd like to thank everybody who participated in this discussion in my group. So dedicated to machine learning methods challenges. So it's very rough approximation of what we discussed. Maybe we lost some bits while running transcript from ChatGPT. But anyway, so there are challenges that are related to enhancing data quality and consistency that can be used for the training of domain-specific foundation model or whatever models. So there is a bridging the gap that addresses that sits between research processes and industrial processes where you need to address issues of larger scale production and what can go wrong there. Of course, development of new materials and devices what was there. Also, improving AI models for multi-scale and multimodal scientific data that might include images, textual representation, graph representation, whatever. So to deal with them more or less naturally. Of course, problem of hallucination and reasoning or absence of reasoning in language models is also a big issue that can be addressed through doing techniques from old times AI or using some reasoning capabilities, trained reasoning capabilities. Okay, optimizing manufacturing processes is also an issue. So that's basically the main themes that we discussed. Maybe there are some others, but we'll recap a bit later and I will do the table and send around. So that's it. Thank you.
Yeah, and I think we'll make these available to all the attendees of the workshop for sure. So you can mull over it and see what you'd like to do with it. Computational methods. Who'd like to present if you want?
Yeah, so the first 2 points revolves around foundation model. So the first point is really so I'm trying to recollect. So it comes from the motivation about the Assoc. Okay, maybe the assumptions of our foundation model. Usually we have a large data, maybe the data is closed, and then we kind of train a large foundation model on it. And then we know that sometimes we train this foundation model and then we use it for our purposes. Yes, it can give solutions, but the solutions might not be accurate because maybe we are only training in a certain space which is not broad enough. And we can give things like hallucination and all these things. Can we have some form of self-awareness foundation model in the sense that it can kind of know in which design space or in which design space where the data is lacking, and therefore instead of suggesting answer, it will actually tap on some tools to do the calculations or maybe experiment automatically and fill the gaps before giving the predictions. So yeah, I guess it sounds very challenging, but this is what we thought there could be a vision, and of course there's obvious technical bottlenecks over here. One is centered around having a database a consistent database or maybe a centralized database that allows you to do this, because in order to build a reliable foundation model, you will need some form of centralized database. And I think in Singapore, in the context of a very integrated society in terms of research community as well, I think we have a coordination means to do that. We have maybe a centralized database, and this will facilitate the building of robust foundation model on that data itself. Yeah, and as for the AI and machine learning methods in terms of innovation, yeah, so it's roughly again the terminology will not be correct, but things like active learning, because the foundation model is able to know which part of the design space is uncertain, and therefore it causing the high fidelity calculations and also experiments to feed the gaps. Right, and potential impact, yes, if our foundation model is really good, then we will have a high hit rate in terms of the predictions. And then that helps our experimental partners to do less experiments. So I think a lot of this about foundation model is about hit rate. So we all use ChatGPT, right? So we all know that at least for the current stage, the things that suggested by ChatGPT, we still need humans to vet it through. Right, so there's always a question about the hit rate. Right, if our foundation model has a better hit rate, then that reduces the amount of experiments. So the second idea also revolves around FM, and it's kind of coming from the thing about having a lot of data, training your FM. Training your FM is expensive, right? So it sounds like okay, if you have a lot of data and like only some of the companies like OpenAI, Google, can have the resources to train the FM, right? So then, then obviously there's some technical bottlenecks. So I think one of the vision or question is that how can we reduce the resources needed for the computations and training models? Yeah, to train the FM model, but maintaining that performance. So I think the bottlenecks that we will probably need to address is efficient AI architecture. So this, I think this we will need to pose it to the AI experts, right? To see whether is there some inherent pattern in materials data that you can leverage on, so that when we design the FM, the foundation model architecture, we kind of make use of that pattern in the materials data, and therefore it reduces the resources. And AI methods wise, I think things like clean computing will come into play, because if your algorithms is designed efficiently, then probably there's less resources and less energy needed to train that model itself. And of course, in terms of transformation and impact, if you're talking about clean computing, then impact becomes on sustainability. So I think this part is maybe less on being able to discover novel materials, but maybe how should I say, maybe a more sustainable way to discover novel materials. So sustainability might be the more important potential impact issue. And the third thing, this is really in the heart of all the computational material scientists. We talk about all the length scales in our modeling and simulation. So when we are doing AI surrogate models for one length scale or one physics problem, there is already a challenge. Is our AI obeying the physical law? So you can imagine if we put 2 or 3 different length scales and 2 or 3 different multi-physics models together, and you train a foundation model or AI on it. Wow, then how do you ensure that this prediction obeys 2 to 3 different physical laws? Right. So this becomes how should I say, a test of the AI model whether it's robust enough. Right. So indeed there will be technical bottlenecks in the sense that in order to validate whether this foundation, sorry, I keep using foundation model, but when we validate this AI model for multiple length scale or multi-physics prediction, then we need different domain knowledge to come in. And I think in Singapore, in the scientific community, we have obviously over here we have various folks with different domain knowledge in the material science aspect and in different scales as well, from the atomic scale and all the way to the engineering and computing scale. So we do have a community to tackle that. And as for the AI methods, yeah, so methodology wise, it could be okay. Maybe one example I can articulate is when we have 2 to 3 line scales, right? Do we want when we have 2 to 3 line scales of data, do we want to have one model that trains on everything? Because it sounds very convenient. if it's able to learn the combinations, then based on the multi-objective kind of requirements that you have, then it can speed up some solutions. Or would you rather make it modular? Modular means you train the machine learning model on each of these particular length scale, and after that you link up together. Because you train modular, the causality link is over there, and hopefully in the causality link you kind of reduce the amount of information that is needed. So there is that two extremes that you can think about, and what is the balance approach to reach these two extremes. Right. Thanks.
Yeah. Thank you very much. I think I need to download the other ones. So we'll go with the structural materials first. Then. Ram, thank you.
Good afternoon. I think we've done a good job of capturing what we discussed. Although structural materials people mostly deal with crystalline solids, most of the metals that you deal with are crystalline. Our thoughts were amorphous. So I mean, I think she tried to capture it as best as she could. One thing to remember is metallurgy is the second oldest profession. And, our civilizations are essentially classified on the basis of metals, right? Copper age, bronze age, iron age. So there is a vast amount of knowledge that we have accumulated over millennia. But this is sort of conventional wisdom sort of a knowledge. It's just so some of the people believe that metallurgy is an art more than science. We know how to make metals, and you're able to fly from here to San Francisco safely thanks to metallurgists quite a lot, or use a lot of other applications. So one of the things is actually both the soft materials people, I think, and to some extent Teck Leong, very articulately described the problems. So if you look at it, right, if you take an alloy that works, so it's the composition that matters. There is processing, there's structure, and in the structure case, we have crystal structures, effects that are there that they play a very important role, grain structures, mesoscopic structures to ultimate performance, right? So if some engineer comes to me and says, look, I need vibranium. So ideally, right, I would like you, Andrey and others, to say, okay, there is this AI model that will give you this. You take this alloy and these compositions, you do this, right? That would be the grand challenge if you can, but that's far away because there is this multi-scale issue also, right? The thing is, so at each level, I think Teck Leong also articulated to some extent, each level you could do with some fidelity, be able to build up a model. But how do you then scale it up in a way that is robust, right? And these processes are highly non-linear, the coupling, and that's why a lot of times only intuition works. So one of the things that we concluded that it may be far too expensive actually to have an AI model that fits this ideal bill. But metallurgy is an art. Maybe Kedar came and said maybe you can use diffusional models to essentially say, okay, these are in these kinds of nickel-based superalloys. I know how it works. Maybe I can input that as one of the things, and maybe many success cases, and then go back and ask it, okay, I need in this context a new alloy, and maybe able to do it. So that is the first one. The second one. So an AI model that can have this essentially have this creative leap, okay, with the diffusion models. Now the other thing is in the second case, this is already Teck Leong mentioned, bridging across length scales. And in fact, we had some corrosion problems that we wanted to attack. 5 years down, we still are far away because the length scale bridging is really a big challenge. Okay, and then one of the problems for metals is also we typically when we use them, most of the times we use in large quantities. So cost is inevitably a factor. So you have to also think in terms of other parameters, not just only scientific parameters, but also economic availability parameters. If you want to get titanium, Americans, for example, they don't have a choice but to go to oppression. These are the kinds of things that that also have to be put in. So I will leave you with that. Thank you.
You have one more, and then we'll pass it over to Kostya for closing comments. Functional materials, please. Okay, right, go ahead.
Thank you. Thank you, Kedar. Okay, I'm representing the functional materials. We have many different types of functional materials, from magnetic material to solar cell materials. And sometimes when they carry the same name, they are actually different materials. So actually there are two Ustyuzhanin, one from AUS, one from the SUTD. Where the AUS one is supposed to lead the discussion, the SUTD one was supposed to do it. Thanks for giving the privilege. Okay, so but in a nutshell, for functional material, our goal can be classified into two categories. One is to create better product with superior properties. And the other is along the way to summarize the new knowledge, new science. And so far, I think we are facing a lot of challenges. One is from the material scientists, we have faced ourselves because we lack sufficient data. In many of the experiments, in many of the simulations, we only calculate the most thermodynamically stable points. But actually, there are many metastable points. They need to become product in the end, but actually we don't know. And more importantly, we actually do not know a lot of kinetic process. We don't understand how fast the process is, how the temperature affects pressure or affects our material properties. And in the end, even for the same recipe, same material, same lab, some people always get a higher efficiency than other people. And actually, we don't know how clear understanding about it. That's why, okay, in addition, there is a barrier to access many data. I think the speakers already mentioned some data just keep secrets for companies, and we don't have access. And finally, one of the biggest challenges for us is as chemists, as material scientists, we do not understand about the AI. Okay, so that's why we have many hopes for the AI and the ML method. The first one is, of course, we need to do together. We needed to provide a better data quality, such as a considered process class related to data, consider metastable states, consider transition states. And then we need to work with the ML, AL experts to ask, are your model really reliable? What kind of data should we provide to you? And is there a universal model as a starting platform for us to get started? I think we really need help and we need to work together. And this gives us many opportunities. One is to improve data quality. So for example, we can have this high throughput experiment where we can ask robotics to do the experiment, therefore to ensure the consistency. We can have a digital twin, which can help us to realize some parameters, which are very important, but we never think about it. And I just learned a new word, new phrase, descriptive engineering. We need to quantify everything if possible, not only for the input, such as the interface area, but also the output about parameters we want to achieve, the property we want to gain. Maybe with the descriptor, the ML can do a better job for us. And also, of course, there are also actions required from a maybe higher layer, from government, from companies. I think we need to make sure the data format is consistent, such that everybody can have access and can use the data. We need to set up protocols to share the data, even buy the data, right? And of course, if we can do everything properly, we can actually sell the data in the future as well. For example, one company is pretty successful, Thermocap, right? So that's input from the functional material group. Thank you.
Thank you, Xiaodong from SCTD. Appreciate that. Okay, so we'll just do the closing at this point. So I'd like to invite Kostya And just to close our thoughts, if you can also at the end tell us how an AI is going to win a Nobel Prize.
First of all, thanks a lot for coming over here. I should say that I was a bit worried when we were arranging this workshop. Lots of people, lots of ideas. Luckily, I think we came reasonably coherent, and we can identify a few buzzwords which we hear the most in this discussion. So let's start with what we have today already. We have the predictive models, which is supposed to work reasonably well, but they're not always, and the reason is that there are insufficient data, not good enough data, the low quality data. That's something which we, so not enough data sharing. That's something which can be probably worked on a background. So, but this is mostly technical challenge, though. We need to identify this as a challenge as well, and hopefully it can be resolved, but not on the scientific level, on the technical level. And something which hasn't been that widely picked up. Only a few speakers today mentioned that faster computational methods amplified and speeded up by artificial intelligence would be required. So like faster DFT, faster molecular dynamics. That's something which is still a question for me. I would say that it's quite important, but only a few people mentioned that. So we need to look closer on this. And then the very large layer of problems which was quite universally addressed in this community is the relation between the composition which we usually all start with to the properties, and that's include many of those issues like multi-scale modeling, the metastable states during synthesis and so on. So the relation of the composition and the properties on the large scale, actually probably even performance as the product. So that's something which is not widely discussed at the moment in the material science and AI material science community, but is the crucial point for all of us. As I said, it has many different aspects, from theoretical multi-scaling to the kinetics of the growth, and I think it might be one of the interesting selling points for Singapore, because of course it's going to be expensive and computationally expensive, but at the same time it would require quite a lot of scientific input. So it's, let's be honest, it's very hard to fight on the par with Google and DeepMind, but this multi-scale issue might be an area where we as a community can contribute significantly, and maybe it should be our buying point, especially as indeed it was probably the most addressed area today. So let me, and then of course the question of the manufacturing, of the being able to synthesize those materials is a separate question. So then there are two more things which needs to be addressed, and so we'll just to say that we're doing this in order to identify the areas where Singapore can thrive and lead the way. So we just need to carefully contemplate on the resources and our capability. So two more things which needs to be addressed is the large throughput experiments, either for data generation or for verification or for both. So it can be just as an active component of the AI development. So just experiments on demand of the particular AI system. So that's still a question, and it's because a lot of problems on the robotics side which needs to be addressed and developed. But I think it's definitely a very interesting and promising opportunity, and it needs to be addressed by someone. Maybe Singapore is the place. And something which is still a good question is the foundational model. So the foundational models clearly holds some promise and a lot of opportunities, but at the same time, we do realize that those are very, very expensive. So that's something which is to think about, to contemplate whether is the place where we can afford to do it and to address it seriously. So, but generally, as a material scientist, as a physicist, I'm really happy that we have this more or less uniformly across the floor. We have this idea that the relation between the final properties and the initial structure is the most important task in material science. It hasn't been addressed properly scientifically yet, and I think we have a lot of potential in this area. Thank you.
Okay, I think that concludes the workshop. Thank you everyone for coming and staying. Really appreciate your inputs, and we will collate all the information. We will send you this stuff when we get around to it. Thank you very much once again.